And then assuming the hypothesis H1 and H2 for every epsilon B has a solution, and then in next theorem we have shown that under this hypothesis H1 and H2 and condition 6, then for this IB possesses an extremal solution on that interval. So under the same condition H1 and H2 with additional condition 6, we have shown that this equation under consideration possesses an extremal solution. These are the references that we have used.
So you have developed a number of theorems to analyze the effect of the factor differential equation.
Yes.
Is there any necessary sufficient condition theorem for analyzing the solution of the factor differential equation?
Not very so.
Is there any necessary sufficient condition of theorem? Just like C and Cauchy Riemann equations. Okay. For analyzing the factor differential equation.
Not
If working on that. If you have only
even that necessary sufficient condition is for the analysis of that function. So I am not considering any function, but we are dealing with the difference equation. And the function f should be of C1 curve, that is set of class of all continuous functions.
You have given 11 theorems. Out of 11 theorems, is there any one important theorem by considering that theorem you can easily analyze the solution like that?
Okay.
Because people want conclusion just by testing once. Like that. Keep on trying it.
Actually, there are some papers in which the RHS EF can also be written in splitting form. Yes. And they are
because it is not possible, it is simply waste of time. If you are going for checking with respect to all these 11 theorems. If you have only one theorem like necessary subject condition, you can easily check.
We have just to show the extra result of this is actually related with the non-linear function, because linear functions have
my point is simple, sir. To analyze the solution, if it is having only one theorem, it is better.
Analysis of the solution has been done with the help of, because the solution is expressly in terms of integration.
Correct.
And therefore, there are some papers actually in which the analysis is actually in the class of the domain of the range of the, if the function here is given on the RHS, it is also defined on the set of all the complex value functions are also defined.
Thank you, sir.
Working on problems is easy, working on theorems is difficult task. Then it takes a lot of time.
ಇಲ್ಲಿ ಮಾಡಿತ್ತ ಈ ಆಡಿಯೋ ಮ್ಯಾಕ್ಸಿಮಮ್ ಆಗುತ್ತೆ Good morning, everyone. So myself, Dr. Monish H. Kantley, Assistant Professor, BGMIT Engineering College, Mudol, Bagalkot District. So today I am going to present on the topic of an efficient wavelet-based numerical technique via Krylov subspace method for nonlinear Kelvin-Gordon equation. This is our main topic. So here basically we are founding the error analysis of the nonlinear equations, especially in the main equation as nonlinear Kelvin-Gordon equation. So I will tell you brief introduction about this. Which is a famous partial differential equation. Kelvin-Gordon equation is solved by using efficient numerical technique based on the Krylov subspace method. So this technique gives a very good approximation of result is obtained and compared through the other methods. I have compared one method of, they are using a decomposition method, some other numerical methods they are using. So that result we got better than those researchers. So mainly this is the main equation. Kelvin-Gordon equation, partial differential equation. We have a second order partial differential equation based on the initial condition as well as Dirichlet boundary conditions. So using this equation, we are founding Hamiltonian or energy equations. That is, we have 1.4. So we have applied this equation by finite difference method, because once we apply the finite difference method, we get the system of linear or non-linear difference algebraic equation, non-linear algebraic equation like Ax equal to B. So these are the preliminaries of the Krylov subspace method. Then generalized methods. This is our Violette precondition method. This is the method of solution. So once we apply the equation, either it is one-dimensional or two-dimensional. So don't bother about. So once we apply the finite difference scheme, we get the Ax equal to B, or Aw equals to F, system of linear equation. If we have a linear equation, we get the linear equation. Otherwise, we get the non-linear system of equations. Using this system of non-discrete equation, we are going to apply the preconditional methods. So we have many preconditional methods, especially we have developed one preconditional method as Krylov subspace preconditional methods. So myself as well as N.M. Bujrike sir, we have developed the one method, that is Krylov subspace method. Using this Krylov subspace method, we are using. So initially first step is we are taking the initialization. Then after initialization, we are replacing that initialization in the given system of equation. So on that system of equation, we are enhancing the stability as well as convergence. Stability matta, then convergence. Then we are calculating the errors. We are calculating the errors. L infinity norms, here we have written. We are calculating 3 errors, L2, L infinity as well as RMS error, root mean square errors. So observing these 3 errors, so compared to previous researchers, so our method is very good. Here I am considering one example. This is the second order partial differential equation, nonlinear partial differential equation called as Kelvin-Gordon equation. So in this equation I am applying the finite difference scheme. After applying finite difference scheme, we get the system of nonlinear equation. So we have conditions, initial as well as boundary conditions. Also we have exact solution. So after finding the results, so this is our previous researcher references. These are the results of previous researchers. So this is our result. So compared to these L infinity as well as root means square norms. So compared to these two years, our result is better. Our result is better, right? So this is one example. Similarly, the graphical representation of the solutions. This is numerical solution as well as exact solution. This is error of the given problem. Also, we are taking the different time steps also. Second example, similarly same thing, we have second order partial differential equation. Similarly, we observe the same L2 error, then L infinity norms, then RMS. So observing these result, our result is better than this. This is a graphical representation of the solution. This is a numerical solution, exact solution. This is the error. Then similarly, third equation. So here also I am considering one more equation. So here also if you observe the results of these three examples, so our result is the better than the previous research. This is the numerical representation of the graphical. While we observing these results, right? So we are finding the three error norms, L2, L infinity as well as RMS. So based on this, so our scheme is numerical stable as well as convergence. So conclusion of this paper is the proposed Jacobian free Newton GMRES scheme demonstrates superior accuracy, efficiency and robustness in solving especially nonlinear problems. Its presence exceeds existing methods in both short and long time simulations, making it is a valuable numerical tool for the solving complex numerical PDEs. So this is our observations. So these are references. These are the references. Thank you. So any questions?
Actually, exact solution is explained here.
Yes.
In the middle.
Okay.
Is there any way to find out that exact solution?
Yes, exact solution. Yes, sir, we have. So especially in exact methods, we are finding this some what we call to find the exact methods, linear to exact, like this, homogeneous. Okay. Because sir, some problems having we are difficult to find exact solution. For example, if you go for PDE, especially nonlinear PDE, for example, I will say one problem, electrohydronic problem or electrohydronic lubrication. Most of the lubrication problem having, there is no exact solutions. In the situation, it is used to find some at least nearer to solution. So that's why these methods are useful. That's why our concentration is where we have finding difficulties to find exact solution, we can approach these methods to those methods. That is our intention.
If exact solution is not there,
Yes.
modify, how do we determine the error?
Yes, sir. Yes, sir. Very good. So we have finding the residuals. Residual nothing but it is nearer to error. For example, if you have Ax equal to B, right, sir? If we have Ax equal to B system of equation, it should be satisfy the equations LHS equal to RHS, Ax equal to F. We are taking a difference of Ax minus F. That is the error. If we don't have exact solution. Actual solution, that's what I'm saying there.
Suppose there is a one nonlinear PDE,
Yeah.
we don't know what is actual solution.
Okay. Okay.
How to find error?
I am saying that if you don't have exact solution, anyway, I am applying some methods we get the solution. We don't know that is the solution right or not. Based on residual norm, we are finding the error. If we have the error as well as this solution having the same errors, so we are conclude that, so our error, you have to get solution. So those solution, we are replacing the initial conditions. What we have assumed the initial condition, those initial condition we are replacing the in Ax equal to b, initial. If the solution is exist based on the residual norms, so then we are conclude that this is the right solution. That is all. Yes, that is graphical. This previous second, sir. Yeah. Yes. No. Some methods, our methods we have taken. Comparing our method as well as exact solution. This is already published paper. What is our method? We are taking. Yeah. Yes. Yes. Any questions, sir? Okay. Thank you.
We'll have one group photo. 7th photo.
chair ಹಾಕಿ ಅಂತ ಈಗ ಅಡ್ಮಿನಿಸ್ಟ್ರೇಟರ್ ಸರ್ ಬರ್ರಿ ಮಂಜು ಒಬ್ಬರು ಬರ್ರಿ ಮಂಜು ಬರ್ರಿ ಮಂಜು ಚೇರ್ ಹಾಕಿ ಕೊಡಿ ನಾವು ಬ್ಯಾನರ್ ಎಲ್ಲ ಇದು ಸಿಗಬೇಕನ್ನ ತೆಗಿಬೇಕು ಇದು ಬರಲ್ಲ ಅಲ್ಲ ಬರೀ ಮಾಡ್ತೀವಿ ಅದು ಒಂದು 4 ಚೇರ್ ಕೊಡಿ ಸರ್ ಪ್ರೊಜೆಕ್ಟ್ ಆಫ್ ಮಾಡಿ ಅದೇ ನೀವು ಆಫ್
as a Ropay Integration Manager at Camping World, based out of Buffalo Grove, Illinois, USA. It's a pleasure to be here at the ICMAA-HM-2025. I'm honored to be here at the International Conference on Mathematical Analysis and its Applications 2025. Today I'll be presenting on wavelets and their applications in science and engineering, focusing on lubrication problems in porous sliders bearing using hard wavelets. So abstract, we will walk through the development and theory of wavelets, limitation of Fourier based analysis, types and multi-resolutions analysis, and application of hard wavelets in solving real-world engineering problems. So this study analyzes how micropolar fluids improve the performance of porous slider bearings. Using hard wavelets, we solve modified Reynolds equations with a better precision and faster convergence. So result shows enhanced damping and the load capacity, especially for inclined bearing. The method sharpens lubrication analysis and helps optimize bearing design. So here quick roadmap of today's talk. We'll begin with that overview and the historical content of a wavelet theory. Then we will examine the limitations of Fourier and STFT, which led to the development of wavelets. I'll introduce the key wavelets concepts, types, and show how they are applied in science and engineering. Finally, we will look at the specific implementation, solving an engineering problem using hard wavelets. So, what is wavelet? So it's a small wave localized in both time and frequency. Unlike Fourier transforms, wavelets helps us to zoom into specific features of a signal, much like analyzing both the forest and the trees. A wavelet is essentially a small wave localized in time and frequencies. So wavelet transforms breaks a signal into a set of scaled and shifted versions of this wave, making them ideal for analyzing signals with both global and the local features. Compared to Fourier transforms, wavelet stores data more effectively, efficiently, and handles sharp changes like edges or spikes much better. It's like looking at both the forest and the trees. The large windows capture the big picture and the small window zoom into one fine details. So let's take a quick journey through the key milestones in wavelet development. In 1807, Joseph Fourier laid the foundation with the Fourier series for signal decompositions. Fast forward to 1909, and Alfred Haar introduced the Haar wavelet, the first for stepwise signal approximations. In 1980, Jean Morlet coined the term wavelet and the development the Morlet wavelet for geophysics. A few years later, in 1984, Grossman and Morlet created the continuous wavelet transform, expanding the time frequency analysis. In 1986, Wes Mayer introduced the smooth orthonormal Mayer wavelet, followed by Ingrid Dutchies in 1988 with the compactly supported orthonormal wavelets. Stephanie Malek's 1989 multi-resolution analysis revolutionized wavelet decompositions. Since the 1990s, wavelets have been go-to tool in fields like signal or image compression, biomedical research, and artificial intelligence. Mathematical transformations help uncover hidden information in signals that's not apparent in their raw time domain form. A raw signal shows the signal over time but lacks key frequencies details. After processing through the mathematical tool, the transformed signals highlights important frequencies, scaled or transient features. One common transformation is a Fourier transform, which decomposes a signal into sine and cosine components, excelling in frequency analysis but missing a time localizations. That's where the wavelet transforms comes in. It captures both time and frequencies, making it perfect for analyzing non-stationary signals or short-lived events. So let's talk about frequency analysis. The frequency spectrum shows the spectral components of a signal, basically what frequencies are present. To analyze this, we use the Fourier transform, which helps us to find and measures how much of each frequency exists in the signal. The equation shows here represents the discrete Fourier transform, we call it as DFT, and the continuous Fourier transforms FT, both used depending upon whether the signal is distal or continuous. In short, Fourier analysis is a powerful tool to understand signal content in the frequency domain. So we have two equations. The left equations, these represent the discrete Fourier transform DFT and its inverse used for discrete signals, whereas the right equations, these are the continuous Fourier transform and its inverse for continuous time signal. So stationary of a signal. Basically, stationary refers to whether a signal's frequency content changes over time. A stationary signal has a constant frequency content. All its components are present throughout the signal duration. In contrast, a non-stationary signal changes in frequency over time. A common example is the chirp signal, where the frequency increases or decreases as time goes on. Recognizing this difference is a key in choosing the right analysis method. So this image illustrates the difference between stationary and non-stationary signals using a time domain and frequency domain plots. The key points: stationary signals, the top row, the components are 2 Hz at plus 10 Hz plus 20 Hz in that one. The characteristics looks like frequency are present throughout the signal. The time plot is constant pattern, whereas the frequency plot clears peaks at the 2, 10 and the 20 Hz. Whereas the non-stationary signals, the bottom the row, the components changes over time, like 0.0 to 0.4 seconds at 2 Hz, 0.4 to 0.7 seconds at 10 Hz, 0.7 to 1 second at 20 Hz. This characteristics basically meant for the frequencies appears in different time intervals. Time plots varying patterns over a time. Frequencies plot is like a broader spectrum, harder to isolate specific frequencies. So the chirp signal, here we see an important example. Chirp signals where frequency changes over time. On the left, the signal increases from 2 Hz to 20 Hz. And on the right, it decreases from 20 Hz to 2 Hz. In the time domain, they look very different. One is rising and another is falling in a frequency. But in the frequency domain, they appear the same. This highlights a key limitation. Fourier transforms only shows what frequencies exist, not when they happen. So signals with the same frequency content but different timing look identical in the frequency domain. That's why time frequencies tool like STFT are essential. Now let's understand why time frequency analysis is important. The Fourier transforms tells us what frequencies are in a signal, but not when they occur. That's a big limitation, especially for non-stationary signals that changes over time. In the real world, many signals like a traffic or speech change with the time, so we need tools that tells us of both what happened and when. An early resolutions was the short time Fourier transformation we call as STFT. It applies the Fourier transforms for short windows, giving us a time frequency representation. But STFT still has a limitation. It's a fixed window size, make it harder to balance time and frequency resolutions. So let's talk about the short time Fourier transformation, like STFT. It was introduced by Dennis Gaber in 1946. Unlike the traditional Fourier transform, STFT analyzes signals in the short time segments using what we call as windowing. So this means we assume the signal is stationary only within each small window. The STFT gives us a 3D view of the signal, showing how amplitude, frequency, and time evolve together. This was a major step towards a localized time frequency analysis, allowing us to study signals that change over time, like speech or music. The equation here reflects this. We apply a window function to isolate each segment and compute the frequency content over time. The short time Fourier transform STFT uses a fixed size window to analyze the signal over time. This creates a trade-off between time and frequency resolution. The left one, the narrow window, gives better time resolution but poor frequency details, whereas the right picture, the wide window, improves the frequency resolution but loses time accuracy. This limitation comes from the Heisenberg uncertainty principle, which tells us we can't perfectly know both time and frequency at once. The images show this clearly. The narrow window captures quick changes in time, while the wide window captures the clearly frequency information. Multi-resolution analysis, or MRA, addresses the resolution limits of a STFT. Unlike STFT fixed window, MRA, that multi-resolution analysis, adapts the window size based on frequency. It uses short windows for a fast, high frequency components and giving better time details. And for the long windows for slow, low frequency parts, improving frequency resolution. This flexible approach makes MRA ideal for signals with a brief high frequency burst and a longer low frequency trends. The wavelet transforms breaks a signal into multiple versions, each representing a different frequency band. Each version captures a specific frequency content over time, allowing us to see which frequencies are present and when. This provides a time frequency localization, which is especially useful for analyzing signals that changes over time, like a non-stationary signals. A wavelet is a small wave used to analyze signals in both time and frequencies. The continuous wavelet transforms, or CWT, does this by sliding and scaling a base function called the mother wavelet. We shift it in the time, translation, and stretch or compress it, others like scale, to study the signal at different resolutions. This makes CWT powerful for analyzing the signals that changes over time. We will get into the detail on that. This is the top formula in the later stages. So the scale, right? In wavelet analysis, scale determines how stretched or compressed the wavelet is. A large scale means a stretched wavelet, good for low frequency and the global patterns. A small scale means a compressed wavelet, useful for high frequency and the local details. So by adjusting a scale, we can zoom in or out on a signal, just like a switching between a wide angle and the zoom lens. And we only need a limited ranges of scales to analyze most signal effectively. So let's briefly walk through how the continuous wavelet transforms of CWT is computed. We begin with the formula here. Xt is the original signal, whereas the psi t minus dot s divided by s is the scaled and the shifted mother wavelet. The dot is the translation parameter, it's a time shift. S is the scale parameter, and psi is the complex conjugate of the wavelets. The steps, we'll go with that steps. Step as S is equal to 1. This gives the most compressed wavelet capturing the high frequency details. And step 2, multiply the wavelet with x times t and integrate over time to compute CWT psi into bracket that dot and s. The third step is like shift the wavelet slightly by updating that dot and repeat the transform. Then step 4, repeat until the wavelet has moved across the whole signal. Fifth step is like, increases to stretch the wavelet, now capturing the low frequency components. And the sixth one each step S splits one row in the time scale map. With all, the last but the least, when all the scales are processed, we begin the full CWT time scales representations. So this diagram compares four signal analysis methods. The time series, top left, we see the signal only in the time domain with the no frequency informations. Fourier transform, top right, this gives us a frequency content but no idea when those frequency occurs. The short time Fourier transform, STFT bottom left, adds some time resolutions by using a fixed side window but comprises on frequency resolution. Wavelet transform bottom right offers the best of both worlds, adaptive time frequency resolutions. It uses a short window for high frequencies and a long window for low frequencies, making it ideal for analyzing signals with both sharp, transient and the slow trends. Now let's move from continuous wavelet transform CWT to discrete version. CWT is a powerful, but it's a componentially intensive because it analyzes the signal continuously over all scales and shift. To simplify, we sample the time scale plane, especially using fewer points at higher scales, because low frequencies need less details. This is often done on a logarithmic grid, typically base 2. However, simple discretizing CWT still leaves redundancy. It's not truly efficient. This brings us to the discrete wavelet transform, or as DWT, which is a true compact representation. It splits the signal into approximation, which is the coarse low frequency part, and the detail, that fine high frequency information. This enables multi-resolution analysis with a significantly reduced computational load. Now let's talk about multi-resolution analysis, or MRA. Many signals, especially real-world ones, require analysis in both time and frequency domains. However, due to Hensberg uncertainty principle, we can't get a high resolution in both time and frequency simultaneously. MRA solves this by using different resolutions depending upon the frequency. For high frequencies, it gives us a fine time resolution but coarse frequency resolutions. For low frequency, it is opposite, good frequency resolutions but poor time resolutions. This approach matches how natural signals behave. Low frequency components usually last longer, and high frequency components tend to occur over short durations. So MRA allows us to efficiently analyze complex signals with the varying features over time. So wavelet applications. Wavelet have a wide range of real-world application across many fields. In terms of typical fields, they are used in areas like astronomy, acoustics, neurophysiology, and optics. Signals and image processing, including music and sub-band coding. Medical and geophysics fields like speech analysis, MRI, earthquake predictions, and radar. Even in nuclear engineering, fractal analysis and turbulence modeling, as well as pure mathematics and theoretical studies, some key use cases include identifying a pure frequencies in a signal, denoising and filtering, especially useful in noisy environments, detecting edges or discontinuities, which is critical in image and signal analysis, finding self-similar patterns in data, and importantly, image compressions and feature extraction, which are the core to many AI and computer vision systems today. So wavelets are not just theoretical, they power practical tools we use every day. This slide introduced the mathematical foundation of the continuous wavelet transformation, or CWT. At the top, we see the wavelet function. This equation shows how we create a wavelet by scaling with the B and shifting with the mother wavelet, IT. The scaling parameter controls frequency while the shifting parameter moves the wavelet in a time. Below we see the decomposition formula. This represents the CW convolutions of the signal f into x with the wavelet function. The results is a set of coefficient w into a and b that describes the signal at various scales and positions. Finally, the plot at the bottom shows how a wavelet can localize a signal in both time and frequency, making it ideal for analyzing signals that change over time. This is what gives a wavelet transform a major advantage over traditional Fourier method adaptive resolutions. So this slide completes the theoretical framework of the continuous wavelet transform by discussing signal reconstruction, admissibility and practical relevance. Decomposition, that's like reconstruction formula. This equation shows that the original signal f into x can be fully reconstructed from its wavelet coefficients w, a and b, provided certain conditions are met. Admissibility condition. This condition ensures the wavelet is well behaved in the frequency domain and is necessary for perfect reconstructions. Zero mean condition, phi raised to 0. This means the wavelet has a zero average, making it ideal for detecting changes or transients in the signal rather than a steady state behavior. The practical applications, this is why the discrete wavelet transform called as DWT, a sample version of CWT, is essential for real-world application like signal compression, denoising, and features extraction. So wavelet are not just a theory, they are powerful tools for modern signals and image analysis. Now let's explore one of the simplest and most foundational wavelet, the Haar wavelet. In 1910, Alfred Haar introduced the Haar wavelet as a basis function of a signal decomposition, making it the earliest wavelet formulation and the powerful alternative to the Fourier basis. At the top of the slide, you can see how a signal, that the black curve, is approximated through a sum of steps functions, each capturing different levels of details. These components come from a wavelet. A basis for L raised to 2 are the Haar function for the orthonormal basis for square integrable functions, that is function in the space L2R. This allows any signal in that space to be reconstructed from Haar components, the averaging and differencing. Haar wavelet transform operate using simple averaging and differencing. The average gives a coarse approximation. The difference captures the detail or variations. Geometric proof, bottom right. So this geometric representation shows successive level of a decomposition. You begin with a full signal, that is fx, then break it down into smoother components and detail at each level, noted as f into 1, f into 2, it goes on, using the basic arithmetic. This simplicity makes Haar wavelet especially valuable for computationally efficient processing like image compression and edge detection. In this slide, we delve into the mathematical structure of the Haar wavelet and how we compute the wavelet transform WT on the discrete grid. The top selection basis function. The function psi t shown on the top list is the Haar wavelet. The general form of the scaled and shifted basis function is here. M is equal to scale index, which controls the resolution. N is equal to shift index, which controls the position. 2m raised to half but ensures energy normalization. On the right side, you see the graphical example of the wavelet functions for different scales and shift, forming the building blocks to analyze any signal. The bottom selection, that is a discrete grid, this diagram shows how the wavelet transform is computed on a discrete grid of scales and a shift. Each colored row corresponds to a different scale level, which is M. Magenta M is equal to -1, which is a finer scale but a higher resolutions. Blue, that is M is equal to 0, and the color green, M is equal to 1, coarser scale, lower the resolution. The dots represents shifted positions, Cn, at each scale, covering the entire time domain at that resolutions. This structure forms the core of the discrete wavelet transform DWT, enabling multi-resolution analysis by progressive zooming in and out over the signal at a various time frequencies resolutions. So this slide explains how multi-resolution analysis. We start with a series of nested spaces Vj, each representing approximations of a signal at a different resolutions. As we go from Vj to Vj plus 1, the resolution increases. The scaling function phi into t shows on the right forms an orthonormal basis of these spaces. It's a low-pass filter that captures the coarse parts of the signals. Each space Vn plus 1 can be split into an approximation space Vn and a detail space Wn, which captures what added at that level. Finally, the functions phi, j, and kt provides the building blocks for the representing the signal at each scale and the position. This forms the basis for wavelet-based compressions, filtering, and analysis. So let's look at the simple example of Haar wavelet decompositions. We begin with the piecewise constant function xt defined over 4 intervals. On the top right, we express it as a sum of a scaling function phi to j, showing how the signal is built from a basic blocks. On the bottom left, we decompose the signal into approximation and detail parts using Haar wavelets. V00 captures the average, which is a core structure, and W00 and W01 added finer details. The bottom right shows an alternative decomposition with the different coefficients, illustrating how we can reconstruct or analyze signals at a multiple levels of details. This is the foundation of a multi-resolutions analysis using wavelets. And again, this diagram illustrates the transformation from a basic box basis to the wavelet basis. At the top, we start with the block like a step function, simple basis that captures the signal blocks. As we move down the diagram, we apply orthogonal transform denoted here by H0, H1 to reorganize the information. These transforms gradually introduce wavelet structures, separating approximations and details at a different level. By the bottom row, we reach a full wavelet basis where the signal is clearly representing across scales in verify 0 and that omega 1 and omega 2 showing both coarse and fine components. This hierarchical transformation is what enables efficient analysis, compression and denoising in a wavelet-based system. And the two-scale relation diagram. This scale shows fundamental two-scale relations used in the wavelet theory. At the top, we see the scaling function verify t, which can be written as a combination of a two-scaled and shifted versions of itself. Then where phi into t and where phi 2t plus where phi 2t minus 1. This defines how we move from a coarse scale to a finer scale using low-pass filtering. Below that, the wavelet function psi t is constructed from the same scale function but with a different, instead of a sum, phi t is equal to psi 2t minus psi 2T minus 1. This operation highlights difference or details, effectively acting as a high-pass filter. These relations are key in building both the scale and the wavelet functions from a simple base enabling multi-resolution analysis. Now let us look at the orthogonal wavelet basis. The goal is to construct an orthonormal basis for each approximation space Vj using function of phi j and kt, which are scalable and shifted versions of a basis scaling functions. These functions follow two scale equations for both the scaling function phi and the wavelet function psi. Note that the wavelet coefficients Gn are derived from the scaling coefficient Hn using an alternating sign pattern. To ensure orthogonality, two key conditions must be met. The filter coefficients Hn must satisfy the inner product condition shown, and the vanishing moments condition ensures the wavelet can represent polynomial trends up to a certain degree. The parameter n, capital N, represents how many of these vanishing moments the wavelet has. The higher n, capital N, the better for analyzing smooth signals. In practice, we can approach things the other way around by choosing filter coefficients Hn that satisfy the two scale equations. Since there is no unique solutions, we can add desirable properties like compact support for localization, regularity for smoothness, and a specified number of vanishing moments for detecting trends. Dubochet's wavelets are a prime examples, and they are designed to have a smallest possible support for a given number of vanishing moments. Here we see the D2 wavelet, one of the simplest Dubochet's wavelets, with its scaling and wavelets functions plotted below. So today I will briefly present how Haar wavelet methods are applied to a micropolar lubrications in porous bearings. By solving a modified Reynolds equations using the Haar wavelets, we achieve faster, more accurate pressure distributed results. The study shows that micropolar fluids enhance damping, stiffness, and load capacity, especially in inclined bearing. This wavelet-based approach improves lubrications, modeling, and help optimizing the tribological performance. So introduction about that, micropolar lubricants offer a better performance than Newtonian fluids, especially in high stress conditions. By improving the load capacity and the film thickness, using the Haar wavelet operational matrix, we solved modified Reynolds equations and found that slider inclination significantly boosts lubrication efficiency. The Haar wavelet is ideal for this due to its compact support, fast convergences, and effectiveness in handling a sharp gradient, making it a powerful tool in fluid dynamics modeling. So in this work, we use the Haar wavelet collocation approach to represent the pressure distribution in porous bearing by transforming the governance PDE into algebraic system using a Haar wavelets basis function. We reduce computational complexity and improve solutions accuracy. The operational matrix method effectively handles boundary conditions and convergences issues, especially in micropolar and fluid problems. Researchers like Dr. Shiral Shetty have successfully applied these techniques, showing its reliability in lubrication analysis. This slide illustrates two configurations of a porous surfaced slider bearings. On the left, we have an inclined slider bearing where the film thickness is denoted by HX varying along with the length X. Enhancing a pressure generation On the right is a flat slider bearing where Hx is a constant. In both cases, U1U represents the velocity of the slider, and the porous layer lies between the slider and the firm base. The domain length is 3 and the AT indicates the time-dependent flow or permeability functions of the porous structures. And this slide represents the governing equations for a micropolar fluid flow. Equation 1 to 3 represents momentum equations along with the x, y and the z directions respectively. Incorporating the viscosity coefficients mu and the micropolar viscosity mu r. Equations 4 and 5 describes the micro-rotation effects with the angular velocity term W1, W2, W3 and the spin gradient viscosity mu r. Equation 6 is the continuity equations. Here U, V, W are the velocity components and P is the pressure. These equations model the complex interaction between flow and the micro-rotation in a micropolar fluids. This shows the governing equations for micropolar lubricants flow in a porous matrix. Equation 14 is the modified Darcy's law that includes the flow resistance and porosity terms. The function F into Cx, Lx and H, and equation 15 captures geometric influence on flow. Equation 16 represents Darcy's velocity Q, which depends on a pressure gradient and a fluid properties. Finally, equation 17 is a Laplace equation for a pressure P dash, ensuring continuity of flow within the porous region. Together, these equations model the complex interaction between microstructures and the fluid behavior. And this slide represents a non-dimensional variable used to simplify the governing equations as shown in equation 24. By submitting these into previous formulation, we derive a non-dimensional form of the Raymond's type equations for inclined porous bearing, shown in equation 25. The functions J dash Ct L dash H dash in equation 26 represents a modified flow characteristics due to porosity and geometry. Lastly, L dash xt defines the film thickness profile, capturing both steady and transient behavior of the bearing surface. And this slide shows the derived Reynolds type equation for a steady state and perturbed film pressures. Given in equations 32 and 33, these are obtained by simplifying the dynamic Reynolds equation while neglecting higher order small terms. Equation 34 and 35 define the pressure related functions incorporating porosity and film thickness variations. Boundary conditions for both pressure types are provided in equations 36 and 37, ensuring the model adheres to physical constraints at the bearing edges. This slide shows how non-dimensional dynamics film forces are calculated for both flat and inclined bearing surfaces, as shown in equation 38 and 39. Using linear theory, equation 40 represents the film forces in terms of stiffness and damping coefficients. The dimensionless form is shown in equation 41. Finally, by separating the real and imaginary parts, we obtain the dynamic stiffness Sxz and damping Cxz coefficients in equations 42 and 43, which are the key to evaluating system stability and performances. So this one represents the Haar wavelet functions and its role in the operational matrix of integrations. The Haar wavelet is defined piecewise within the interval 0, 1 as shown in equation 44 with the values depending on the subintervals beta and rho and the sigma. The variables depends on m is equal to 2 raised to k, where k is the wavelet level and the k is the translation index. These definitions are essential for constructing the operational matrix which enables efficient numerical integrations in engineering problems. So this one introduced the scaling functions h1a, which is a base of a Haar wavelet family. It is defined as 1 in the interval 0, 1 and the 0 elsewhere as shown in the equation 45. Next, integrals involving Haar functions are introduced using the notations Lj and Qa and LRjQa, which represents integral of the Haar functions and their combinations. These are essential for constructing the operational matrix of integrations. Equations 48 and 49 provide specific computed forms of these integral using the Haar definitions from earlier. These help simplify the process of integrating functions in numerical methods. So the methods of a solution, this outlines the solutions methodology using Haar wavelets. We start with equation 52 where the second derivative ya is approximated as a sum of Haar functions multiplied by unknown coefficient bj. Based on boundary condition, this equation is integrated twice, either from 0 to or from a to 1. To obtain the expression for ya and y put a, y double put a, equation 53 introduce the collocation points aj where the differential equations will be satisfied. These are evenly spaced across the interval 0 and 1. Using these collocation points, we substitute the Haar functions approximations into the differential equations. This converts the problem into linear or nonlinear algebraic systems of a size 2L into 2L, which we solve to determine the Haar coefficient bj. Finally, equation 54 gives the expression for ya after integrating the series representation twice, considering the boundary value alpha and beta. And the pressure solution, this slide shows a non-dimensional pressure distribution P along with that film thickness direction X for different parameters. In the top left graphs, we see the variation of a pressure with Tc is equal to 0.3 and the wavelet resolution level Z is equal to 1.5. The top right graph shows a similar pressure curve with the same Tc is equal to 0.3 but at a slightly different setting of Z is equal to 1, helping us see the influence of a wavelet resolution. The bottom graph also explores pressure distribution with Tc is equal to 0.3 and Z is equal to 4, further increase in the resolution. Across all plots, the pressure rises to a peak in the middle of the domain and drops symmetrically towards the end. This is typical behavior for lubrication problems under steady-state flow, demonstrating the validity and smoothness of the numerical solution obtaining using the Haar wavelet method. The color gradient from the blue to yellow represents the variation in pressure magnitude visually, highlighting the region of a maximum load carrying capacity. This graph illustrates the variation of a non-dimensional constant load bearing capacity denoted as a W bar W R with respect to the profile parameters lambda across different values of the characteristics length bar L and R. We keep the coupling number CR is equal to 0.5 and the permeability parameter F is equal to 0.1 and F is equal to 0 constant for all cases shown. The plot shows that as lambda increases, bar W and R initially rises. reaches a peak and then begins to decline. For higher values of a bar LR, the maximum bar WR is higher. This suggests that non-Newtonian effects become more significant as bar L and R increases. In particular, compared to the Newtonian baseline bar LR is equal to 0, the load capacity improves notably when bar LR is non-zero. This clearly demonstrates that increasing the characteristics length enhances the load carrying capacity of the bearing system, likely due to stronger viscoelastic or microstructural contribution from the non-Newtonian fluid behavior. This plot shows how the non-dimensional dynamic stiffness variable denoted bar S dyn varies with the profile parameter lambda for different values of the characteristics length bar L and R. We have fixed the coupling number CR is equal to 0.5 and the permeability parameter F01 throughout this analysis.
Hello.
Hello. Hello, sir. Good morning, sir.
Hello.
Hello. Good morning, sir.
Good morning. Morning. So can
Welcome.
you hear me now?
Students.
Ma'am, can you hear me?
You read, sir. We need prepare again.
Hello.
Hello, good morning, sir.
Good morning, ma'am.
Good morning to everyone. I would like to introduce our next session speaker, Mahantesh Basurajappa sir, Department of Mathematics and Physics, Texas and AM International University, Laredo, Texas. Sir has completed his MSc from the MSc in Mathematics from Kuvempu University, Shimoga, and under the guidance of Dr. B.J. Girisha sir, he has completed his PhD. Sir, research areas, interest areas include applied and computational mathematics, hydrodynamic instability problems, modeling and computation of nanofluids, machine learning, and statistical analysis. Sir also published many papers in international and national journals. So with this brief introduction, I would like to welcome Mantesh Basurajappa sir for this session. Thank you, sir.
Okay, ma'am. Thank you, ma'am. Thank you for the nice introduction. Ma'am,
I request Professor Shiral Shetty sir to chair this session.
Thank you. Okay, sir. Thank you, sir. I think I hope you can hear me. I think you can also see my screen. Can you please confirm me? Okay, so today, I will be talking about.
You can start.
Okay, sir. Okay, all right. Thank you, sir.
Yes, sir.
Okay. So I will be talking about two of my research projects in this work, in this presentation. And first, I would like to thank Shiral Shetty sir for giving me this opportunity to talk in this conference. Before I start my work, let me tell you my background. As mentioned in the introduction, I did my master's, bachelor's, and as well as PhD from Kuyempu University. And I started my work at Christ University in the year 2016. And I was there for 5 years. And later in the year 2021, I moved to University of Texas to do a postdoctoral fellowship. And the last fall, I joined the Texas A&M International University as a faculty member. Given this background, let me tell you my research interest. I specifically work on developing mathematical models and methods to analyze the physical phenomena, specifically the problems involving fluid motion. And these are my research areas. So in this talk, I will be introducing two of my projects which I carried out during my postdoc period, and as well as my tenure at TAVI. So this is the project one I will be talking about. This is a joint work with the Professor Dharwad, who was my postdoc mentor and also expertise in stability analysis problems. So in this project, we basically investigated the linear stability analysis and non-linear stability analysis by using the energy method for a really linear convection configuration, utilizing Kelvin White fluid model. So that is very interesting in this project. And let me tell you briefly what we have done in this case. We did the linear problem, which is heated from the below and as well as started from the below, and we computed the threshold values by using linear and nonlinear theories. Before I jump into the project one, let me give the basics of the relevant convection problem, and then I will briefly talk about the Kelvin White fluid model, and then I will jump into the problem. The instabilities in the fluid model, they are all around us. We could see from the nature and as well as in industries, and they appear on all spatial and as well as temporal scales. I will talk about this in the next slides, how they appear in different scales. And they are caused by the multitude of phenomena, like they may be caused by the temperature gradient, they may be caused by velocity gradient, due to the magnetic field, due to the internal heat source. There are various phenomena will cause the fluid instabilities essentially. And they have a great impact on various applications, that including in engineering technologies and as well as environment. We know that the stabilities will play a good or important role in weather forecasting. Various applications are there when we talk about the fluid instabilities. These are the examples of instabilities. I just rushed through these slides. As you can see, it is a shear-induced instability. This is also called as Kelvin-Helmholtz waves. And these waves formations are caused by shear stress, that is by the velocity gradient. What happens is the cloud moves in two different velocities basically. Due to that difference in the velocity of the two layers of the cloud, there is a formation of cells like this, or a instability in the cloud flow, and this is called as a Kelvin-Helmholtz instability or shear-induced instability. And this is thermal instability. This is a naturally ongoing process is 24/7 in the earth mantle due to the temperature gradient. As you know that like the earth mantle has a supreme temperature, and on the surface of the earth we have a like the cold temperature. Due to the temperature difference, there is thermal convection, and there is a convection. Convection is ongoing every time in the earth mantle, and this is caused by the temperature gradient, by the way. And the similar setup in the laboratory, this is called as a relevant configuration. What basically we do in the laboratory is we heat the fluid layer from the bottom, and we cool it from the top. What happens is, like you could see in this picture, there is a formation of cells. You see there is a nice hexagonal shapes of the fluid, and we are going to see like what critical temperature difference will cause the motion of the fluid in this pattern. So that is what we study in the thermal instability. And the present project, like project 1, we discussed the thermal instability issue in the configuration of a relevant problem. And we have next instability, which is free surface instability. This is caused by the surface tension. And I think this you could see in the various the forums, like the kids will like to see this kind of like the toy models, which is the instability of the fluid. The fluid what they have taken is also called as a ferrofluid, or it is also called as a magnetic fluid. Underneath of this fluid container, there is a magnetic basically. So due to the magnetic effect, there is an instability in the fluid system. So in various museums, like they will keep this sort of a toy models that children like to play. So this is known as a magnetic instability. There are various instabilities. I would like to like just introduce these pictures. And so in the project 1, we are talking about thermal instability. That is basically caused by the temperature difference between the two layers. That is called as a relevant convection problem. So what is relevant convection problem? It is a type of flow that is driven by the differences in the temperature gradient. Okay. So due to the temperature differences, there is a differences in the density. So due to which convection occurs, or maybe fluid flow occurs in the system. As you can see in the toy model, we have a fluid in the container, and we are using the fluid from the bottom, and we are cooling it from the top. What happens is, like if I heat the fluid layer from the bottom, the parcel of the fluid near the lower plate, or maybe in the bottom plate, gets hotter, and the fluid parcel, which is sitting on top of the container, will be colder now. And as we know that water liquid will be less denser, and this is the high denser liquid. Now we are in a situation that high dense liquid is sitting on top of low dense liquid, but nature will not allow it due to the buoyancy force. The high dense liquid will try to sink it down, and due to the gravity and because of the lighter liquid, the low dense liquid will try to move up. However, this phenomena will be opposed by the fluid properties like viscosity, and other fluid properties also will resist this type of motion. At the end, like at a certain critical temperature differences, the buoyancy force will dominate over viscous forces, and then convection commences basically. So the type of motion occurs in the cyclic pattern. We could see the formation of the cells in this manner, and these cells are called as Karnatak cells. And what are our research questions basically? So we need to know what is the temperature difference will cause the fluid motion like this. And essentially this motion will lead to the turbulent convection later on as we keep on heating the fluid from the bottom. So we need to know what the critical temperature will cause the convection first. So that's the first research question. So we need to know the critical temperature difference that triggers the instability of the fluid. And we also need to know how do fluid properties influence the onset of instability, like viscosity, thermal conductivity, thermal expansion coefficient specifically. How do they contribute to the onset of instability? So that is also another important question. And the third question would be the type of the flow what we are going to consider, like the nature of the flow medium. like the types of the geometry, whether it is a clear media or a porous media. If it is a porous media, what type of a porous material, whether this geometry is inclined or it is a vertical, whether it is a horizontal. So all these properties will also impact on the fluid instability. So to answer these questions, like these are the three important research questions which we study in thermal instability problems. To answer this question in mathematical analysis, we come across the a parameter in the mathematical analysis, that is thermal Rayleigh number. So this thermal Rayleigh number measures the impact of buoyancy force and as well as the viscous force. If you could see the definition here, alpha is the thermal expansion coefficient and delta T is the temperature difference. This is what we need to know. And G is the gravity and H is the space. It's a distance between the two plates basically. If you think of, we have another plate on the top of the fluid. And mu is the kinematic viscosity and kappa is the thermal diffusivity. And we need to know, you see, like we have the fluid properties, we have the distance between the two, these two plates, that is also play an important role in the convection. And we also have the very important property that is temperature difference. So studying this parameter, one can know like how these properties of the fluid, the flow medium, the critical temperature difference will impact on the fluid instability. So this is our key parameter in the problem. So we need to know what Rayleigh number will influence the instability or will keep this fluid system stable. So we need to know what the Rayleigh number should be for a stable system and what Rayleigh number should be for an unstable system. So we need to know basically the Rayleigh number value for a given problem. For the classical Rayleigh problem with a physically realistic boundary conditions, we have a threshold value for triggering the instability, that is 1707. So if any value crosses this threshold value, you could see a convection or you could see a instability in the fluid model. That is from the linear theory basically. Okay. And in the next slides, I will be showing some animations which depict how the convection commences as we increase the Rayleigh number in the fluid model. You could see in this animation, it is like I have taken from this website just to illustrate how convection occurs for a different Rayleigh number. You see, they have conducted the experiment taking the water as a fluid in a cylindrical container which is horizontally sufficiently long, and they heat the fluid from the bottom and they cool it from the top. It's a Rayleigh configuration. So when Rayleigh number is 1000, you see the temperature difference. The fluid is not moving basically, but heat is diffusing upward direction. So heat is moving the vertical direction, but there is no fluid motion yet because the Rayleigh number is less than the threshold value. You remember that the threshold value is 1707. So this is very much less than the threshold value. So in this case, the fluid is still stable and there's no motion at all. And there's only heat transfer and it is occurring only in the z direction or a vertical direction. And in the next slide, I will be showing animation when Rayleigh number is equal to 1800. So this is like above the threshold value, you see convection begins. Okay, so what I mean by convection begins is there's a fluid motion which is occurring as the periodic cells, like throughout the plate you could see the formation of cells in this manner. Okay, so however, so this motion is still a laminar motion because if you see the two layers, the parcel of the fluid is not interacting with the other cell basically. So it is still a laminar convection. So for the Rayleigh number which is equal to 1800. So this is when like when temperature difference is around 14 degrees Celsius or something, like we get the Rayleigh number to be 1800 for this experiment. And when Rayleigh number is equal to 1800, convection commences. For a very large number, of a Rayleigh value. So you could see the turbulent convection. You see the fluid, like how it is moving, the parcel of this fluid layer, this Bernard cell will interact with the other one, so vice versa. So there is a chaotic motion. So we have a turbulent convection now at very high Rayleigh number. So this is what we are trying to see in the theoretical model as well. So we need to know the threshold values of the Rayleigh number at which convection commences. So that's the main research question in the model 1. So having said about the Rayleigh convection problem, now I will move to the Kelvin-White fluid model. So this is another very important aspect of the problem which we have considered. The Kelvin-White fluid model, so it will describe the fluids with both viscous and elastic properties. And the application of the fluid model including polymer solutions, biological fluids, and geophysical fluids. For an incompressible fluid, we have the velocity equation, the momentum equation look like this. So along with the viscous effects, we also have a time-dependent elastic responses. So where lambda is the modulus coefficient, that captures the retardation effect of the viscoelasticity, and it is also known as Kelvin-White coefficient. This model was used by the Russian researchers a lot in the 1970s and as well as 1990s by Oskolov and other collaborators. So they studied this model in the direction of the existence and regularity of the solution. They also concluded that in one of the study, so this term, it is also known as a Kelvin-White term, will act as a good regularization term for the solution of the Navier-Stokes equation. So that is what they have proved. And how do we think this model as a momentum equation? Like one can think in this way, like we have the momentum equation where sigma is the Cauchy stress tensor, where dot denotes the material derivative. The sigma, the Cauchy stress for this Kelvin-White fluid model will be given by the equation 1. As you can see in this constitutive equation, we also have the time-dependent elastic responses. Not only the viscous effect, we also have the viscoelastic effect. However, if you see the time derivative, it is not a objective derivative we have. So we have local derivative. So this was pointed out by Damasio et al. in the study in 2016. It is not objective derivative. The Pavlovsky proposed another model. So this thing, in fact, this is the first model which was given by Pavlovsky. That is nowadays it is known as Kelvin-White fluid model. So he invented this model to describe the flow of water containing a weak solution of polymer. However, we don't have still an objective derivative, but we have a material derivative now. But in the literature, we already have a elastico-viscous liquid model with the objective derivative. Okay. So you can think of momentum balance equation for the Kelvin-White fluid model in these directions. So we have a local time derivative. However, so this model was used by Professor Brienstraben recently, maybe probably past 5 years. He is studying this fluid model in the perspective of instability problems. He had made a number of studies. So some of these studies are given here. This is the very first model he introduced in the relevant convection configuration. And after that, he himself studied various different models by considering various physical aspects into the model. So, and also recently, in one of the monograph, he has an exclusive chapter on Kelvin-White fluid model and their applications, and as well as various fluid model to investigate thermal instability configurations with porous media, different porous material, with local thermal equilibrium impact, and local non-thermal thermal equilibrium impact. So he introduced various models in this model. So what he had concluded is, for a theories like linear stability analysis, the model 1 is adequate, and that is suitable for performing the stability analysis. That is what he concluded in these studies. So this is a motivation for us to consider this fluid model to perform a stability analysis in the configuration of a relevant problem. In addition, a solute equation, like we are not only heating the fluid layer now, we are also sorting the fluid layer with a Soret effect. So that was the motivation behind the project 1. So having described the motivation and the behind the study, now I would like to introduce the physical model of the problem 1. This is the physical model. So we have two plates and we have a fluid layer. The fluid layer is Kelvin White non-Newtonian fluid model. And we are heating the fluid layer, and also we are sorting the fluid layer from the bottom, and we have taken the no-slip velocity conditions. And this is how the Cartesian coordinate system is used, where the plates are measured horizontally in the x and y direction. We assume that plates are sufficiently large in the x and y directions, and the distance between the plates is going to be h, and the z is measured vertically upwards. Gravity, of course, is like it acts downwards. So we know the phenomena already, how the convection commences. For this physical model, and we have taken the isothermal boundary conditions as I mentioned before, like we have constant isothermal boundary conditions. Here, the TL is larger than TU. That indicates we are heating the fluid layer from the bottom. Likewise, the CL, that is concentration at the lower plate, is also larger than CU. That also indicate that we are salting the fluid layer from the bottom. So we are analyzing this mechanism. It's a very interesting mechanism because the heating the fluid layer is a destabilizing effect. On the other hand, we are salting the fluid layer. So it's a stabilizing effect. You see there is a combination between the stabilizing and as well as destabilizing mechanisms. So that gives the very important and very interesting results. So for this physical model, we have the following governing equations. We have, of course, this system is for the incompressible fluid. We have taken the Oberbeck-Bosniak approximation. The Oberbeck-Bosniak approximation tells that the density can be treated constant everywhere in the momentum equation, but not at buoyancy force term. Like when it is multiplied with the gravity, it needs to be a function of the temperature and the solute concentration. In fact, with the pressure as well, but in this case, we have taken it as a function of temperature and as well as solute concentration. In other places, the density can be taken as constant. So we have taken the Oberbeck-Bosniak approximation, and the thermal equilibrium also we have taken, and we also have a solute concentration equation. In the solute concentration equation, if you see, we have a term. This term indicates the thermal diffusion effect, or so-called Soret effect. I start from the momentum equation. We have the Kelvin White fluid term here that captures the time-dependent elastic response of the fluid. Okay, and we have the convective term, we have the pressure gradient term. So this is the viscous term. There is a term here. This is called as a damping term. So our previous speaker spoke about the damping effect on the microfluid model. So we also have a damping term here. This is also known as the Ekman damping. It's a linear damping effect where beta is the damping coefficient. Kappa D is the thermal diffusivity, and kappa C is the thermal solutal diffusivity, whereas kappa S is the Soret coefficient. The density over here in the buoyancy term is taken as a function of temperature and solute, and we are taken as a linear relationship here with the temperature and as well as solute. You see, as temperature increases, density will decrease. As solute concentration increases, the density will increase. So we are capturing both phenomena in this model. And this governing system is defined on the domain omega. As I mentioned in the model, the plates are taken sufficiently large along x and y direction, and the distance between the two plates is going to be h. So this is the domain of the problem, and we have the following boundary conditions. So we have no slip boundary conditions for the velocity at both walls, and we have a constant isothermal boundary conditions for the temperature, constant iso-solutal boundary conditions for the solute concentration at both walls, 0 H. And this is our governing system. Now, this stability problem, so you can think of, we have a dynamical system now. So what we do in the dynamical system, we find the solution that is initial solution, or in other words, like we find the equilibrium point, and then we impose the perturbations around the equilibrium point and then see how the dynamical system behaves. The similar approach we follow for this particular problem as well. So we find the basic state solution. It is also called as a background state solution, or you can you can think of the animation number 1. So there is no motion in the beginning. The heat is diffusing only in the vertical direction. That is the background state. So we find the basic state solution, or a conduction solution, thermal conduction solution, or in this case thermal conduction as well as solutal conduction solution, and then we impose the perturbations, and then we see how the perturbations evolve around the time, around the equilibrium solution. That's what we're going to see. So we find the basic state solution now. In the basic state solution, velocity is 0, there is no fluid motion, and the temperature and as well as the solute, they diffuse just only the z direction, that is our vertical direction, therefore the function of z alone. With these, the governing equations become ordinary differential equations. So here just ordinary differential equations now. So as given in equation 6, with the corresponding boundary conditions are given here, they are simple boundary, differential equations one can solve easily, and we get the basic state solution. Now around this basic state solution, we impose the perturbations, and then we perform the stability analysis. So in this project, we did 2 types of stability analysis, linear stability analysis and non-linear stability analysis, and I'm going to talk about that in the later slides. So we first impose the perturbations to the basic state solution as given in equation 8. You see the U sub B, TB, PB and CB are perturbation solutions. They are function of Z alone. And we are imposing the perturbations now. So capital V, theta, phi and little p are perturbations for the velocity, temperature, solute concentration and pressure respectively. And we assume this perturbation to be periodic in nature, and for linear stability analysis we assume to be very, very small. For non-linear stability we assume that they are going to be, they have a finite amplitude basically. Okay, they are not going to be small, we are going to include the non-linear terms, so but we take the finite amplitudes of these perturbations. Now, introducing these perturbations into our governing system and following the standard non-dimensionalization approach, we get the following system, which is given in 9. You see this is the perturb system now, so we have the variables, all our perturbation variables, and we have a number of parameters, the physical parameters. The Prandtl number we have Kelvin-White fluid parameter, we have Ekman damping number, we have solute Rayleigh number, we have a Lewis number, we have a Soret number. More importantly, we have a Rayleigh number. So this is what we need to figure it out, like what this Rayleigh number could be, which satisfy the system to trigger the instability. Okay, and this system is defined on this domain, and these are the initial boundary conditions for the problem. You see we have a 0 Dirichlet boundary conditions at both the walls, and these are the initial conditions for the perturbation variables. As I mentioned in the introduction, like I'm going to perform 2 stability analysis now, a linear approach and as well as non-linear approach. The standard linear approach could be, we are going to linearize the system around the basic state solution, assuming that the perturbations are small, meaning that the interactions of two perturbations are going to be ignored. To put it in a simple words, we are just going to omit the nonlinear terms in the system 9. And then we are going to see how these perturbations evolve around equilibrium solution or the basic state solution. So we linearize the system, and next what we do is, like the pressure variable, it's a very bad variable because it has no its own equation. So it is sitting, like in the momentum equation. So what we are going to do is we eliminate the pressure, and we are just going to account only the z direction velocity component, because that is most important, because fluid motion is happening in the z direction. So we just account the w component of the velocity vector. And then we use the normal mode approach because the resulting system is going to be linear, and that allows us to use the solution as given in this equation. So like because the perturbation variables are assumed to be periodic in nature, so that allows us to use the normal mode approach or a Fourier mode approach as given in this equation. So here the script f represents all the perturbation variables like the velocity, temperature, solute concentration and pressure. It look like this. In this expansion, the sigma is the growth rate, where sigma r is the real part of the growth rate. If it is positive, the fluid system is unstable. If it is negative, so the fluid system is going to be, the stable because the perturbation decays. And if it is equal to 0, we get the marginal stability curves. Whereas the kx and ky are wave numbers in the x and y directions. So following the standard procedure, we get the following differential eigenvalue problem. So if you see the system, we have additionally two parameters here, the sigma and the k squared. The k squared is the total wave number, whereas sigma is the growth rate. Okay. So if you look at the system, it is a fourth order in velocity, second order in theta, and second order in phi. So we have a 8th order differential equations here. But if you look at the boundary conditions, we have only 6 boundary conditions. For the closure, we have to impose 2 more boundary conditions for the velocity, depending on the surfaces, like the walls. If they are free, we could include 2 conditions on both walls. If they are rigid, they are physically realistic. So we can also include 2 conditions for the at both walls. Then the problem is going to be closed. So we did the same thing. We included the free boundary conditions and as well as rigid boundary conditions for the closure. And we solved this eigenvalue problem using Chebyshev tau method to satisfy this system, and we got the Rayleigh number. What next? So once we get the Rayleigh number, we have to minimize with respect to the wave numbers to get the critical value. So we have to solve the minimization problem with k square. So k square is the total wave number. And this minimization problem we addressed by using golden section search method. That's a pretty easy method. One can use it to minimize the Rayleigh number to get the threshold values for the linear instability. Now from the linear theory, we get the threshold value only to trigger instability. But we don't know anything about the stability basically. So we don't have the stability thresholds. So that we get from the nonlinear theory. So in this project, we have used the energy method to conduct the nonlinear stability analysis. It's a very famous method to perform the nonlinear stability analysis. We are going to include the nonlinear perturbations. There is no restrictions on the perturbations now. We are going to account the finite amplitude of the perturbations. And this method is also known as integral method. So this is a very good book for the energy method by Brian Straugan. So if somebody wants to learn the energy method and to use it for the stability problems, I would recommend this book as a starting point. And this is the picture of Brian Stragan. I took it from his website. Sorry, I forgot to put the credit here. Now, I would explain you like the energy method, how it works. So basically, we're going to use the same perturbed system. We take the dot product of this equation with velocity perturbation, and we multiply theta to this equation, and we multiply phi to this equation, and we integrate over the periodic cell, or over the volume, or over the domain, okay? So once I integrate, we get the following energy identities. So these are the energy identities I get by performing the operations what I mentioned just before, and these are called as energy identities. So this is from the momentum equation, and this is from the temperature equation, and this equation is from the solute concentration equation. Here we have, so this notation is L to norm, that is norm, L to norm, and we have an inner product here. So we have these identities, they are called as energy identities. They are square integrable functions basically. And looking at this, the terms with the derivatives, we are going to construct the energy function involving the perturbations. If you look at the energy function which we have constructed here, it is basically a combination of kinetic energy plus some potential energy which is caused by the temperature perturbation and as well as solute concentration perturbation. In addition to these terms, we also have some parameters like eta 1 and eta 2. They are known as coupling parameters that we are going to choose optimally to have a best threshold value. And if I differentiate this equation with respect to time t, I get the following equation for total energy function, which involves all perturbations. Now one can show the energy function decays exponentially very easily. I will go quickly. That is, you see, I can write this equation by adding all these equations. I can get the following energy equation now. So in this energy equation, I have two terms mainly, the production term and the dissipation term. You see, we have all positive definite terms here, and these are non-positive terms. And that is why, like I'm naming them as production term and the dissipation term. There is a competition between the production and as well as dissipation term. Now I'm going to see, I'm going to rewrite this equation, and I will introduce the RE now, the script RE, that is the maximization of I over D, where H is the space of admissible functions, which satisfies the boundary conditions plus periodic boundary conditions plus incompressibility condition. Now introducing this into this equation, we obtain the following inequality, and one can show that this factor is positive when RE is greater than 1, that's a simple thing. And also one can show that D equal to, the script D equal to, sorry, script D is greater than or equal to pi square B times E by using Poincare inequality. Now plugging these two quantities into the energy inequality, what we have in 21, we get this following inequality. And integrating this, we obtain this expression. Look at the equation 24. So what it says? So it says the total energy of the perturbations decay exponentially fast for all the initial data provided. So that we call it as a global stability. Okay, the condition RE greater than 1, the condition RE greater than 1 ensure the stability of the system for all the initial data. That is what we have proved. Okay, so the condition RE greater than 1 guarantees the global nonlinear stability of the basic state solution. That is what we have showed. Now we need to know what this RE is, because we need to make sure this script RE has to be greater than 1. Okay, so for that we have to solve this maximization problem. So that will lead you Euler-Lagrange equations by using the calculus of variations, and we have the Euler-Lagrange equations imposing the incompressibility constraint also. We have the equation 25, the system 25. So following the normal mode approach, as like we did in the linear theory, we get the following differential eigenvalue problem with the eigenvalue RT. RT is the eigenvalue here now. So we can solve this eigenvalue problem by using Runge-Kutta method or a Chebyshev-Tau method or a spectral collocation method or any other method. In fact, we could find the Rayleigh number value that satisfies this differential system, and one could find the threshold value. Now for the nonlinear stability, the threshold value would be minimizing with respect to k square, that is total wave number, and also we have to maximize with respect to coupling parameters. You remember we took the coupling parameters in the total energy function, so we have to choose them to have a sharp stability threshold. Okay, so we have to maximize them. We have to maximize the Rayleigh number with respect to eta 1 and eta 2. And again we did this maximization problem using golden section search method. So these are some numerical results. You see we have a marginal stability curve from the linear theory and as well as from the nonlinear theory. You see the blue line is from the linear theory and the red line is from the nonlinear theory. So what this graph says is, any value of the Rayleigh number above this blue line, the fluid system is going to be unstable. On the other hand, any Rayleigh number below this red line, what you could see here, the fluid system is going to be stable. However, there is a region between these two lines that is marked in the green color. So this region is called as a subcritical instability region. So we don't know whether fluid is stable or unstable in this region. Okay. So sometimes this region expands or contracts, that depending on the parameter values of the problem. So we studied, like how other parameters impacted on the instability region, subcritical instability region by varying other parameters. You could find in the paper. I'm going to present now the plot of critical Rayleigh number from the linear theory versus solute Rayleigh number for various values of Kelvin-White fluid parameter. So that's a very important parameter of the model. As you can see, as Kelvin-White fluid parameter increases, the critical Rayleigh number also increases, meaning that it requires more temperature difference to cause or to trigger instability, meaning that the retardation property of the Kelvin-White fluid model stabilizes the fluid system. So it acts as a stabilizing agent basically. So you see the stable region is going to be expanded as lambda increases. So the impact of the retardation effect of the Kelvin-White fluid model stabilizes the fluid system. That is what we saw in these graphs. The left graph is for in the absence of Soret effect, and this is in the case of presence of Soret effect. You could also see the impact of the Soret effect now. You could see in the presence of Soret effect, the Rayleigh number is smaller, meaning that the Soret effect acts as a destabilizing effect. Okay, it destabilizes the system basically. And these are the some contour plots and as well as the 3D surface plots here for the velocity perturbation, that is the W component. As you can see, we plotted these graphs in the presence of Ekman damping and in the absence of Ekman damping. So in the presence of Ekman damping, the perturbation velocity, the magnitude of the perturbation velocities are smaller, meaning that the Ekman damping acts as a stabilizing agent in the fluid system. So that is a very, very important effect of the damping effect. You could also get the the result of Darcy term, because when you have a Darcy model, you would get the similar type of a term which we have in the case of a damping effect. Okay, so the Darcy parameter also will have the same effect as the damping parameter what we have in this model. Now with this result, I would like to show like some of the other works, like on the Kelvin-White fluid model and the stability analysis. So this is our recent work, which we did on LTNE porous media with the magnetic field effect. We considered two porous materials like sander sandstone and aluminum metallic foam. We also considered the physically realistic boundary conditions, and we performed the linear and as well as nonlinear stability analysis. We have used the spectral collocation method to solve the eigenvalue problems. We found the very, very interesting results in this paper. So if somebody is interested in, like, I would recommend reading this paper. And also this paper, this is basically on the third grade fluid model, the similar approach, but the fluid model is different. Whereas in this work, we did the penetrating convection, meaning that the convection triggers by the internal heat source now. Okay, so it is also like has very, very interesting results due to the internal heat source. So we discussed the effect of 4 different form of internal heat source distributions on the onset of convection. And we also discussed the transition from the stationary mode of convection to traveling mode of convection. Very interesting results are there in this paper as well. Now I will quickly move to the project number 2. I will just brief the work. So in this work, we studied the dynamics of the nanofluid in the conical region of the cone disk device. And later on, motivated by this work, and later on, like one of my PhD student from Christ University, Bangalore, Anaga John Susan, she did a wonderful job. We together did like 4 problems on stationary cone disk system. It is not just a rotating cone disk system, but a stationary cone disk system where the fluid motion occurs due to the inlet device, like a swirler. So we got a very, very interesting results, like from this model as well. And we jointly worked with Igor V. Shevchuk, German mathematician. He did a lot of work on cone disk devices. We did a lot of, 4 problems basically, 4 projects on the stationary cone disk devices considering various physical mechanisms. So the cone disk system, you see the geometry here, like the physical setup of the rheometer. We have a cone, this is the cone, and we have a disk surface, or you can think of it as a plate, and the inverted cone touches the apex, its apex on the disk surface. So that creates a small conical gap between the cone and as well as the disk. So we place the fluid specimen within this conical gap, and we study the velocity and as well as temperature profiles within this conical region. So if somebody is interested like in this geometry and the flow models, I would recommend reading this book by Igor V. Shevchuk. He had a lot of models on rotating flows, like especially on the disk surfaces, and there is one specific chapter on cone disk device. Okay, so that is the motivation when I read this book, like I referred that model and as well as another paper by Mustafa, and we extended the work for the nanofluid model, and later along with my PhD student, we worked on stationary cone disk devices. This is the physical model. We have a disk surface, we have a cone, as I mentioned before, and these 2 devices are rotating basically with the different angular velocities. This is how the geometrical the cylindrical coordinate system is taken horizontally in the radial direction and vertically in the z direction and axially in the v direction. And we have taken the isothermal boundary condition and as well as iso nanoparticle volume fractions on both the geometries. And we are rotating these 2 geometries in 4 different configuration when cone is static and disk is rotating, when disk is static and cone is rotating, when both are rotating in the same direction, when both are rotating in the opposite direction. So we studied the problem with these 4 different configurations, and our goal was to see which configuration will provide maximum heat transfer. That was the goal basically, and we studied this model for the nanofluid model. And these are the governing equations, the standard governing equations. We have continuity equation, momentum equation, and we have considered the two-phase Brownian model. We have the Brownian motion and as well as thermophorus system, and this is the conservation of nanoparticle volume fraction equation. And we developed the self-similarity transformations by using Lie group theory, and this is the self-similar model. And we solved this two-point boundary value problem using mathematical function, MATLAB function BUP5C, and we presented the result in terms of similarity variables by varying the different parameters of the model. And we studied like 4 different configurations of the model by varying other physical parameters. I will present some of the results. So this presents the radial velocity profile for 4 different configurations. As I mentioned, you see the first model, the model 1 represents the rotating cone and static disk, and the second model represents static cone, rotating disk. The third model is about co-rotating cone and disk, and these are counter-rotating cone and disk. As you can see in the model 1, where cone is rotating and the disk is static, you see there is a radial outward flow near the cone, there is a radial inward flow near the cone surface because cone is rotating, and then since the disk is static, like we have a radial outward flow basically. Whereas we could see the opposite phenomena when cone is static and disk is rotating. You see the green curve. When both are rotating, you could see there is a radial outward flow near the cone and as well as the disk surface. And in the middle conical region, we have an inward flow. The similar flow we have for the model 4 also, model 3 also, but the magnitude is small, so it looks like a straight line, but it's not the case. This is pretty much same as the black line. So that is how the velocity profile behaves. This is the dimensionless velocity, that is radial velocity profile. And this is the dimensionless temperature profile for 4 different configurations. As you can see, the model 1 has the highest temperature profile, and the least is going to be the second model, and the other 2 models stands in between them basically. We studied the Nusselt number, and we observed which model provides the maximum heat transport by constructing the regression models in the papers. And this is the profile, the temperature profile by varying the 2 important nanofluid parameters like the Brownian motion parameter and the thermophoresis parameter. So it is a well-known result in the literature. As we increase the thermophoresis and as well as the Brownian motion, the temperature profile increases. That is due to the chaotic motion of the nanoparticle within the fluid, and as well as the fluid always move towards the outer, the outer fluid will, outer particle will try to move towards the lower outer particle. So we could see the jump in the temperature profile even in the case of dimensionless temperature profile. And this is all about the results of the second model. We have a very comprehensive results in the paper. If somebody is interested, can refer those papers basically. So having said this, let me provide my perspectives in this slide. So the nonlinear stability analysis provides the general framework for stability and completely captures the physics of the convection phenomena. So energy method is a wonderful method to perform the nonlinear stability analysis to get a threshold values for stability of the fluid system. And this model, like the first model, can be extended to the various physical configurations, such as one can study the impact of variable fluid properties, like the fluid properties which are function of temperature and as well as pressure will be one of the interesting problem. And both projects can be extended to other classes of non-Newtonian fluid models. Uh, one can use the machine learning techniques to get the better prediction values. So many extensions are possible. So I'm open to do the collaborations. If anybody is interested in these two projects, I'm happy to, have collaboration with interested ones. So with this, I would like to stop here and I'm open to take questions if you have any. Thank you so much. Shiral Sati sir, can you hear me sir? I think I'm on time, right?
ಹಾಯ್
Hello sir, sir ಚೆನ್ನಾಗಿದ್ದೀರಾ?
ಹೆಂಗಿದ್ಯಪ್ಪ?
Sir ಚೆನ್ನಾಗಿದ್ದೀನಿ sir, ನೀವು ಚೆನ್ನಾಗಿದ್ದೀರಾ sir?
ಇದನ್ನ ಓಪನ್ ಮಾಡೋ, ಇದನ್ನ ಕ್ಲೋಸ್ ಮಾಡಿ.
Video sir. Okay, just a minute sir. Can I stop sharing sir?
ಯಾ.
Okay.
ಎಲ್ಲಿ ನಿನ್ ಮುಖ ತೋರ್ಸಪ್ಪ.
Just a minute sir. ಗೊತ್ತಾಗ್ತಿಲ್ಲ, ಯಾಕೋ ಬರ್ತಿಲ್ಲ ಇದು.
ಓಕೆ.
I'm sorry, ಯಾಕೋ.
Sir, thank you very much for accepting our invitation and made this grand success. Your talk
Thank
was
you so
very
much sir.
informative.
Thank you so much sir
And
for
you
inviting me
lots
and
for our students. Wholeheartedly, thank you very much.
thank you so much sir for invitation. Thank you sir, Giri sir also.
ಥ್ಯಾಂಕ್ ಯು.
Any questions from the audience?
Yeah.
ಎನಿ ಕ್ವಶನ್ಸ್?
Sir, I have one question.
Yes sir, please sir.
Sir, Giri sir has started applying the wavelet
Wavelet,
operators for
yeah.
solving the equations.
Yes sir.
So you can suggest us if we are using
you-
the wavelets for solving what you are using the equations.
Eigenvalue problem sir.
ಸ್ಟೆಬಿಲಿಟಿಗೆ. ಶೂರ್.
Can we apply for your problems?
So wavelet transformation so use ಮಾಡಬಹುದು ಸರ್, ಮಾಡ್ಬಿಟ್ಟು ಮತ್ತೆ ಲೀನಿಯರ್ ಸಿಸ್ಟಮೇ ಬರುತ್ತೆ. ಆ ಲೀನಿಯರ್ ಸಿಸ್ಟಮ್ನ ಮತ್ತೆ ಇದು ಯಾವುದು QZ ಅಲ್ಗಾರಿದಮ್ ನ ಯೂಸ್ ಮಾಡ್ಬಿಟ್ಟು ಸಾಲ್ವ್ ಮಾಡಬಹುದು.
Yes sir, we will be in touch with that, and then we are very much keen interest to apply our wavelet operators for solving your equations, sir.
Sure sir. Thank you so much.
Yes sir, thank you sir.
Yeah.
ಓಕೆ. ಮಂತೇಶ,
ಸರ್ ಹೇಳಿ ಸರ್, ಚೆನ್ನಾಗಿದ್ದೀರಾ ಸರ್?
ವಿತ್ ಯುವರ್ ಪರ್ಮಿಷನ್ ನಾನು ನಿನಗೆ ಫಸ್ಟ್ ಇಂಟ್ರೊಡ್ಯೂಸ್ ಮಾಡಬೇಕಾಗಿತ್ತು ಆಡಿಯನ್ಸ್.
ಇರ್ಲಿ sir, ಇರ್ಲಿ.
ಈಗ ಇಂಟ್ರೊಡ್ಯೂಸ್ ಮಾಡ್ಲಾ?
ಓಕೆ. ಎಸ್ ಸರ್.
Sure.
ನೀವೇನು ಹೇಳ್ತೀರಾ ಅದು?
Listen to me. So, I think you know who is the speaker. Professor Mantesh, working in Texas A&M University. A huduga, just an ordinary, and he came from very poor background. He was my MSc student, very poor background. ನನಗೆ ನನ್ನ PhD ಇಬ್ಬರು ಸ್ಟೂಡೆಂಟ್ಸು ನನಗೆ ಸಜೆಸ್ಟ್ ಮಾಡಿದ್ರು, ಈ ಹುಡುಗನ್ನ PhD ತಗೊಳ್ಳಿ ಸರ್, ತುಂಬ ಬಡತನದಲ್ಲಿದ್ದಾನೆ ಹುಡುಗ, ಬಟ್ ಜಾಣ ಇದ್ದಾನೆ, ತಗೊಳ್ಳಿ ಅಂತೇಳಿ. ಅವಾಗ ನಮ್ಮಲ್ಲಿ ರಿಜಿಸ್ಟ್ರೇಷನ್ಗೆ PhD ರಿಜಿಸ್ಟ್ರೇಷನ್ಗೆ 4 years ಅಡ್ವರ್ಟೈಸ್ಮೆಂಟ್ ಕೊಡಲಿಲ್ಲ. 4 years ವಿತೌಟ್ ಹ್ಯಾವಿಂಗ್ ಸಿಂಗಲ್ NPA ಫೆಲೋಶಿಪ್ ಆ್ಯಂಡ್ ವಿತೌಟ್ ರಿಜಿಸ್ಟ್ರೇಷನ್ 4 ವರ್ಷ PhD ವರ್ಕ್ ಮಾಡಿದ ವಿತೌಟ್ ಹ್ಯಾವಿಂಗ್ ರಿಜಿಸ್ಟ್ರೇಷನ್. ಬಟ್ ಆಫ್ಟರ್ 4 years he got registration. 4 ವರ್ಷ without fellowship, without earning single NP, he did research work without having registration, even registration. So andre that shows his dedication. He dedicated a lot and finally he got registration. At the end of his thesis, he has published around 50 publications in very reputed journals like Scopus and Web of Science journals. Such a wonderful person. ಒಂದ್ಸಲಿ ಅವನು ಇಂಥದ್ದನ್ನು ಮಾಡಬೇಕು ಅಂತಂದರೆ ಈಸ್ ಗೋಯಿಂಗ್ ಟು ಸ್ಟಿಕನ್ ಆನ್ ದಟ್ ಒನ್. ಸೊ ಆ ಒಂದು ಹಠ ಇವತ್ತು ಮಹಾಂತೇಶನ್ನ US ಒಬ್ಬ ಫ್ಯಾಕಲ್ಟಿ ಮೆಂಬರ್ ಆಗಿ ವರ್ಕ್ ಮಾಡಲಿಕ್ಕೆ ಕಾರಣ ಆಗಿದೆ. ಬಿಟ್ಟರೆ ಬೇರೆ ಯಾವುದೇ ಅದೃಷ್ಟ ಇನ್ನೊಂದಿಲ್ಲ. ಅದಕ್ಕೆ ಬ್ಯಾಕ್ಗ್ರೌಂಡು ಅವನ ಹಾರ್ಡ್ ವರ್ಕ್. ಸೊ ಐ ಆಲ್ವೇಸ್ ಬಿಲೀವ್ ಇನ್ ಹಾರ್ಡ್ ವರ್ಕ್. ಅದಕ್ಕೆ ಬೆಸ್ಟ್ ಎಕ್ಸಾಂಪಲ್ ಮಹಾಂತೇಶ. ಈ ಡಿಡ್ ವೆಲ್, ಈಸ್ ಡೂಯಿಂಗ್ ವೆಲ್. ಈಗ 3 ವರ್ಷ ಆಯ್ತು ಅವನು USA ಹೋಗಿ. ಸೊ ತುಂಬ ಚೆನ್ನಾಗಿದ್ದಾನೆ, ಚೆನ್ನಾಗಿ ವರ್ಕ್ ಮಾಡ್ತಿದ್ದಾನೆ. ನನಗೆ ನನ್ನ ಸ್ಟೂಡೆಂಟ್ ಅಂತ ಹೇಳ್ಕೊಳ್ಳಿಕ್ಕೆ ಹೆಮ್ಮೆನೂ ಕೂಡ. ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು ಮಹಂತೇಶ.
ಥ್ಯಾಂಕ್ ಯು ಸರ್. ಇಲ್ಲ ಏನಂದ್ರೆ ಸರ್, ಕೆನ್ ಐ ಸೇ ಸಮಥಿಂಗ್ ಸರ್?
ಏನಪ್ಪ?
Can I say something, sir? Yeah. ಏನಂತಂದ್ರೆ ಗಿರೀಶ್ ಸರ್ ನನಗೆ ಇಂಟ್ರೊಡ್ಯೂಸ್ ಮಾಡಿದ್ದು ಫ್ಲೂಯಿಡ್ ಮೆಕ್ಯಾನಿಕ್ಸ್ನ. ಸೊ ಅವರು ನಮಗೆ ತುಂಬ ಪೇಷನ್ಸಿಂದ ಹೇಳ್ಕೊಟ್ಟು ಕೆಲವು ಮಿಸ್ಟೇಕ್ಸ್ ಎಲ್ಲ ಮಾಡಿದ್ರು ಕೂಡ ತೀಡಿ ಕಲಿಸಿದ್ರಿಂದನೇ ನಾವು ಇಲ್ಲಿ ಬಂದ್ಬಿಟ್ಟು ಇಲ್ಲಿ ಕೆಲಸ ಮಾಡೋಕ್ಕೆ ಆಗಿದೆ ಅಂದರೆ ತಪ್ಪಿಲ್ಲ ಸರ್. ಇಟ್ಸ್ ಆಲ್ ಬಿಕಾಸ್ ಆಫ್ ಯುವರ್ ಬ್ಲೆಸ್ಸಿಂಗ್ ಆ್ಯಂಡ್ ಬಿಕಾಸ್ ಆಫ್ ಯು ಸರ್.
ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು.
Thank you so much, sir.
ನೀನು ನಾನು ಬಿಟ್ಕೊಡಂಗಿಲ್ಲ.
No, sir. No, that's the fact, sir. That's the fact, sir.
ಓಕೆ, ಆಯ್ತು.
Thank you, sir.
ಒಳ್ಳೇದು ಮಾಡೋ, ಚೆನ್ನಾಗಿರು.
Okay, sir. Okay. Thank you, sir. Bye.
Bye.
I thank Mahantesh Basarajappa sir for sharing his valuable words, and also I thank Shiral Shetty sir for chairing this session. Also I extend my gratitude to BJ Girisha sir for introducing and saying wonderful things about Mahantesh sir. Thank you, sir.
Thank you, Anaga. Now without any late, let's begin the next session. Now I would like to call Mutalik Desai sir to, I would like to call Madhu to continue the session.
Thank you, Sustri. Good morning, everyone. Welcome to session 4. The chair of the session is Dr. P.V. Mutalik Desai sir. Sir has completed of MSc from Karnataka University, Dharwad, PhD in the field of finite element and wavelet-based numerical solution for differential equation and their applications. Sir presently working as professor and head of the mathematics department VTU and guiding 4 students for PhD work VTU. Sir, research paper published in the international journals, reputed journals like Spinjovan, Taylor, Francis One. Sir attended 6 international proceedings and 4 international conferences. I respect to chair this session, sir. Welcome, sir. Welcome, sir.
My friend Dr. B.J. Girisha is a professor in Coimbatore University, Shimoga. He is very perfect, effective, and popular in the field of research in mathematics. Though he is very perfect and effective, but it is my sincere duty to tell something his great achievements during the research work. He completed MSc in 1997, PhD in 2003, and apart from that, postdoctoral fellow from USA in 2015. His area of research includes computational fluid dynamics and wavelet theory. Some of the awards of recognition, if I collect them, ranked 5th in nationally and 654th globally in the area of mechanical and aerospace engineering in 2025 edition by ResearchCom. UGC nominated member for the Academic Advisory Committee of Sri Venkateshwara University. Prestigious Sir C.V. Raman Young Scientist State Award in the field of physical and in mathematical sciences for the year 2020 initiated by the government of Karnataka. Recognized as one of the topmost scientists in the world from Stanford University, USA, rankings continuously in the year 2018, 19, 20, 21, 22, 23, and 24. He is a life member of National Academy of Sciences, Indian NASI in 2021. He has been awarded with prestigious Raman Fellowship 2015 to pursue postdoctoral research in USA. And from 1997 to till date, his research experience are 26 students have been awarded PhD and 7 more are working under his able guidance. And apart from that, 11 students are awarded MPhil degree from them. His scientific publications include 478 in total. You just observe 478 in total, both in international and national journals, 229 in science journals, 365 Scopus indexed journals. These are some of the jewels if I add to his crown. Apart from that, Google Scholar citations, if I quote them, citations are 14,020. I think it is, which we cannot imagine at this moment. Each H index is 65. I-10 index is 29. Citations are 10,660. Again, H index is 58. Invited talks and special lectures delivered by him are around more than 100 in both international and national conferences throughout the India and abroad. Research projects, he has got 5. Out of these, 3 major research projects of worth rupees 35 lakhs have been completed, sponsored by UGC and DST, and 1 minor project of 0.5 lakhs sponsored by UGC. He is a principal investigator for the DST sponsored first program of worth 55 lakhs. I am trying to have a bunch only to cover all his achievements, prestigious awards, his research experience and so on. He had given only few of the top technical publications here, but apart from that, as I know, and we are very lucky to hear, to see, to observe, to enjoy, to got some knowledge from each present lectureship. Thank you, sir. You are welcome.
Thank you very much. A very good morning to you all. First of all, I would like to thank the organizers of this conference, especially to Professor Shiral Shetty sir and Professor Patil sir, Ramane, Devanal madam, Asha and all. And I am very happy Lokesh is here with me. So because he is from functional analysis field, but I am in fluid mechanics. Intersection is a little difficult, but even though he is sitting in front of me, really it's a privilege. So here my topic is dimensional analysis and non-dimensionalization. Why I have taken this topic as a special lecture? So I have delivered this lecture so in different places, okay, like in Andhra, Tamil Nadu, so even in NIT, Arunachal Pradesh and some IITs, and wherever I go, usually I used to deliver this lecture first time, and then after this I used to deliver another lecture that is on similarity transformation. These 2 lectures are very favorite for me. I don't know, it may become favorite to you or not. So I like these 2 lectures pretty much because we are all doing research in fluid mechanics. There usually we do some mistakes. My intention is we have to avoid those simple mistakes. These are very simple mistakes, but we do simple mistakes in our research. So by taking the advantage of those simple mistakes, I think those who are working in the field of fluid mechanics, they may know the name Asteropantacotaresis. Asteropantacotaresis is a mathematician. So he used to write the comments on those mistakes. Simply 1 page or half a page, he used to write the comment on our mistakes, what we already published, okay, what we already published. On those papers, he used to write simple comments, only half a page or 1 page, and he used to publish as a paper. Like this, he has published more than 1,000 papers. More than 1,000 papers he has published with simple comments in a half a page or 1 page maximum. So actually, by that time, in 2016, I think, 2016, ಇದು ಏನಂದ್ರೆ ಕನ್ನಡದಾಗ ಹೇಳಿದ್ರೆ ಕರೆಕ್ಟ್ ಅನ್ಸುತ್ತೆ, ಈ ಶನಿ ವಕ್ರಿಸೋದು ಅಂತಾರೆ ನೋಡಿ, ಹಾಗೆ ಅವನು ಎಲ್ಲರ ಜೊತೆನೂ ಕಮೆಂಟ್ ಮಾಡಿಬಿಟ್ಟು ಪೇಪರ್ಗಳನ್ನೆಲ್ಲ ಪಬ್ಲಿಷ್ ಮಾಡ್ತಾರೆ, ಡಿಮಾರಲೈಸ್ ಮಾಡಿಬಿಟ್ಟಿದ್ದ. ಸದ್ಯ ನಮಗೆ ಒಕ್ಕರ್ಸ್ಕೊಂಡಿರಲಿಲ್ಲ ಅಂತ ಖುಷಿಯಾಗಿದ್ವಿ ನಾವು. So he has not come to our papers, but in 2016, I got one mail from the editor, chief editor John from Journal of Nanofluid. I am also one of the editor to that journal. He wrote me one mail. So Girisha, we have received some comments on your paper by Astero. He wrote like this, so please reply to this. Really, by the time I got afraid because he wrote the comment, you know. So I got afraid and simply I ignored that mail for 15 days. Then again he wrote a mail. Girisha, please don't sit silently. You have to give the response. Otherwise, people will think in different manner. It means it's an escapism. Okay? If I am not going to give the response to that mail means it becomes an escape. Okay? That's why he wrote me again. We two are very good friends. So myself and John Philip. So once again he wrote me the mail. Then I took it as serious and I called my student, those who are involved in that paper. One Krishnamurthy and another one Prasanna Kumara BC. Now he is a professor in Davangere University. He is working as a professor in Davangere University. Those two are my students, Krishnamurthy and Prasanna. I called them. They came to my home. By overnight, we took, we sat to each other and we start to work on it. That paper was on dusty fluid. Okay. So, we verified that on the comments of Astero and we found that finally by 12:30 night, we find that we are correct and his comments are wrong. Then we got confidence and we wrote the comments on that paper. Okay. I already published one paper in that journal. Again, Astero published one paper in the same journal based on my paper by writing simply comments. Again, I wrote the comments based on the comments of Astero in the same journal. Again, I published the paper in the same journal with one page. So, in that paper, I wrote him like anything because I was disturbed by that time. So, if you know the thing correctly, clearly, then you have to comment on any person, on any work. Otherwise, you should keep quiet. Okay? So, I wrote, so Astero is a misleading mathematician in the world. You should not consider his work, words, because, so he has commented like this and detailed calculation provided here and you can verify it with anyone. So, his comments are wrong. So, then they have accepted and published my paper and this is one of the paper. Is it possible to open this PDF? Look at that. This one. Click on it. Click on it. No, so escape kodi, escape put click ಮಾಡಿ. First page go. First page. He click ಮಾಡಿ. ಇಲ್ಲ ಫೈಲ್ ಇದೆ ಇದರಲ್ಲೇ ಫೈಲ್ ಇದೆ ನಾನು ಅದಕ್ಕೆ ಸಿಕ್ ಫೈಲ್ ಕೊಟ್ಟಿದ್ದೆ
ಓಪನ್ ಆಗ್ತಿಲ್ಲ ಸರ್
ಆಗ್ತಿಲ್ವಾ ಓಕೆ ಲೀವ್ ಇಟ್ ಫುಲ್ ಸ್ಕ್ರೀನ್ ಮಾಡಿ ಓಕೆ So then I thought, so I have to give the awareness to my students as well as my colleagues, those who are working in the same field. So what are his comments? Simply on dimensions. Because usually we used to climb Reynolds number, Prandtl number, Nusselt number, different non-dimensional numbers, you know. So usually we are going to claim them as non-dimensional one. Okay, but he found that in some results, Reynolds number, Nusselt number and those numbers have some dimension. That's why his argument is, you claim that it has a non-dimensional one, but it is dimensional. That's why whatever your claim in that paper are wrong. That's why you have to take back that paper, like that. One more thing, why dimension remains in the paper? That is another lecture. So I have delivered one full day in Karnatak, in this university. So that is based on similarity transformations. Because choice of similarity transformation leads to, actually in the literature, we have written, so REX, local Reynolds number, local Nusselt number, okay, local like that, because there you have the parameter X in that one. That's why you used to call them as local numbers. But anywhere in the literature, there will be no local Reynolds number, no local Nusselt number or any local numbers. Usually only Reynolds number, only Nusselt number, only skin friction coefficient, like that. There will be no local. We used to call them as local because in those numbers X remains. Why X remains? Because of choice of wrong similarity transformations. Then how to derive, that is different story. Okay, I'm not going to talk about that one because I already delivered the lecture in the same campus. Okay, now here I'm going to concentrate on dimension analysis. Okay, let us see. See, what is dimensional analysis? You know, dimension means velocity has its own dimension, meter per second, okay, time, second, so length, meter, like that. So everything has its own dimension. Whatever the variables appear in the governing equation, they have their own dimension, right? So that is nothing but dimension. Now we are going to reduce them into non-dimensional. Non-dimensional means, so velocity, we are going to reduce velocity to non-dimensional means dimension must be unit, 1. It doesn't contain meter per second. Like, so u is meter per second. I am going to define new velocity u star. U star is equal to u divided by some u bar or capital U. So u is also velocity, u bar is also velocity, uniform velocity. The dimension of those two is same. So meter per second, those two get cancels, then remaining is 1. Like that we are going to non-dimensionalize the equation. By non-dimensionalizing those, you are going to get special characteristics like Reynolds number, Nusselt number, Prandtl number, different kinds of non-dimensional numbers. They must be numbers. We are going to call them as Reynolds number means it must be a number, it should not involve any x variable in that. Similarly, Nusselt number means it must be a number, it should not involve x anywhere. But we are going to hide the variable remain in the equation into these kinds of non-dimensional numbers, like in Reynolds number, like in Nusselt number, like that we are going to hide those numbers and we are going to call them as non-dimensional numbers. But we should not do that one. It is a wrong concept. Then what to do? How to verify? First, you are going to consider a formulation for your research means you have to verify the equation for the dimension. Means left hand dimension should be equal to right hand dimension. Then only your formulation is right. Otherwise, your formulation going to be wrong. How? Because I am going to do one new paper. For that, I am going to refer some any XYZ papers. I am going to take that paper and I am going to study that paper and so what he has considered and what he has studied. Then for that paper, I am going to add some new parameters. Like if we neglect the magnetic field, I am going to add magnetic field. If we neglect the radiation term, I am going to add the radiation term. Then I am going to do my own calculation and so I will get the corresponding results. Once you add or delete any terms in the equation, by that time we should check for the dimensions, whether the dimension is balanced or not. Once the dimension is balanced, then go for the other calculation. But most of us, including me, we are going to ignore the, verification of dimensions in our research paper. But the first preliminary aspect is, first we have to check for the dimensional analysis, means whether the equation is fully defined or not. Defined means the left hand side dimension must be equal to the right hand side dimension. Okay, then we go for the further calculation. Let us see how to calculate the dimensions. Okay, so these are the some examples of dimensions: density kg per meter cube, velocity meter per second, kinetic viscosity, like that. If you want the detailed dimension analysis, please download this file. I had a file. Okay, download this file. In that file you can find the dimension for whichever the variables appear in your research problem, especially so where you are using the Navier-Stokes equation, energy equation, mass equation, there sure. So you will find all the variables and their dimensions. Okay, that is the simple. I have collected simple examples. That's it. So I have taken heat equation because we have to verify, whether they are dimensional or not, or balanced or not. See there, heat equation means del U by del T is equal to alpha into del square U by del X square. It is very simple one-dimensional heat equation. Is it right? So I am going to substitute the dimensions for the corresponding variables. Like U is there and T is there. Okay, U is there and X square is there. By substituting the dimensions and upon simplification, you can see that the left hand side dimension is meter per second square. Similarly, the right hand side dimension is meter per second square. Means the equation is balanced and your considered equation is correct. If you find any difference in the dimension, left hand side and as well as in right hand side, that shows that your formulation itself is wrong. Okay, that's why we have to verify for the dimensions, right? Next, how to do the non-dimensional one, that equation. To non-dimensionalize this equation, I have considered these non-dimensional variables. Like I told you earlier, I am going to define new velocity U as U star, and it is defined by U by U. U is velocity and capital U is also the velocity characteristics, means the dimension of U star is meter per second and capital U is also meter per second. Then those two get cancelled and the remaining dimension is 1, means it is now non-dimensional 1. There will be no dimension. Okay. In the similar manner, see, by substituting those in the equation, you are going to get the non-dimensional equation in this form. Here, there will be no dimension in LHS as well as in RHS. It is purely non-dimensional equation. So for that, I define time variable and previously velocity, and here length variable x, position variable x in different manner. Okay. So I substituted in the original equation. Finally, I got this equation as a non-dimensional one. Like this, you must verify the dimensional analysis for your considered problem, your considered research problem. Okay. So I have taken as an example, another example, wave equation. Which one? Huh. S4? With this one? Meter per? So here T square is there, in denominator. Time, it denotes time. Time square is there. That's why it becomes second square. So it is taken in numerator, that's why s to the power minus 2. And here velocity meter per second, no square, only U is there. That's why it is meter per second. So totally it becomes meter into meter per second cube. In heat equation, same thing happened. See, this is second, time, and this is velocity, U. If you are going to consider T as temperature, so then it's different manner. Here I have considered it as a velocity. velocity. I have taken it as a velocity. Otherwise, it will become Kelvin. Okay. So I will show you that equation also. In the next slides, you will see. Right. So there, meter per second square. For wave equation, meter per second cube. The dimension becomes, see here, you got meter per second cube in LHS as well as in RHS. So means the equation is perfect. Then so reduce it into non-dimensional one by defining the non-dimensional variables like u as same in the previous problem, and then so your x as well as t, and substitute in the equation, original equation. Then you see that the equation becomes so non-dimensional equation. Okay. Now I have taken momentum equation. I mean research problem, simple research problem. Okay. So very simple problem. Here you see that this is the momentum equation. For different assumptions, we obtain the momentum equation in this manner. Original momentum equation you know. For some assumptions, I mean restrictions on the flow, you are going to get this equation as a momentum equation for unsteady flow. So I have submitted all the dimensions for the equation, all the dimensions, whatever the dimension for velocity, for length, for time, so for kinetic viscosity, for everything I have submitted the dimension mu by rho, density, everything. Okay. So submitted. There you see this is the detailed, I mean units of different parameters appear in the equation. Finally you got the dimension as meter per second square is equal to meter per second square. Means the momentum equation is perfect. Means for my restrictions on the flow, because you know how to restrict the flow. For Poisson's flow, you are going to consider that the flow is one directional. Okay. And you know the width of the channel. You don't know the depth of the channel as well as length of the channel. Means so you are going to assume all the parameters are not functions of x and y. So velocity is function of only z, and the flow is steady. Means it is not a function of so time. Like that we are going to assume different restrictions for the flow. For this restrictions, for some restrictions, this equation, so you obtain meter, I mean whatever the restrictions you have considered the flow are appropriate. Otherwise you are going to get different dimension. That itself shows your equation considered is wrong. Okay. So now again I non-dimensionalize the equation by defining the non-dimensional variables like u, so I mean time, x, y and everything. So then it reduces to this equation purely as a non-dimensional one. Okay. In the similar manner, so here energy equation. So now you come to your part. Okay, temperature is there. So this is one of the energy equation considered for the research problem under some restrictions. Again, we have some restrictions. For those restrictions, okay, for those restrictions, so this is the energy equation what I got. For those I have submitted all the so dimensions to the equation. Okay. So then I verified that. So you get Kelvin per second as a so unit in both the sides. Left hand side is Kelvin per second and right hand side is Kelvin per second. It means that so the energy equation considered for your problem is 100% right. Otherwise it's going to be wrong. You simply, so you can decide yourself that if the dimension does not matches right hand side as well as left hand side, you can decide by your own that your formulation itself is wrong. That's why first you have to verify for the dimensions of the equation. Then do the non-dimensional process. Right? Okay. So again by non-dimensionalizing the equation, we are going to get the non-dimensional equation in this manner by defining the non-dimensional variables. Right? So see, I am not going to expose any names of the authors here. Just I have taken some examples. What Astero published papers, based on Astero published papers, I have collected some results. How he has published the papers. See, this is one of the, this is the, I mean definition of Reynolds number, rho nu, u by, adanta rho ul by nu, ul by nu. So nu means mu by rho. So here the dimension must be 1, means Reynolds number dimension is 1. That's why it is called as non-dimensional numbers. Similarly, Prandtl number, similarly Nusselt number, all are non-dimensional. 1 means dimension must be equal to 1. You have to verify for your results whether they are non-dimensional or not. Otherwise, you should not claim it as a non-dimensional number. Okay. So see how we are going to fail. So doing these things. This is for Prandtl number. Observe there, dimension is 1. After substituting the whatever the units in those appear in Prandtl number, you are getting the Prandtl number unit is 1. Means our claim, we used to say they are non-dimensional, means it is appropriate. Okay. Next, so similarly Nusselt number, similarly Grashof number. Okay. All are non-dimensional. We can verify easily. Eckert number, right? So on Hartmann number, all are non-dimensional. Whatever the numbers we defined, all are non-dimensional one. You can easily verify them, right? Using those quantities, units. Now, common mistakes observed in non-dimensional numbers. So this is one of the author. I am not going to expose his name. It is not right also. One of the author, very popular author, he has published one paper. Astero commented on his paper due to these numbers. Simply he wrote these numbers authors claimed as non-dimensional one, but actually they are not non-dimensional, they have dimension. That's why author's claims are wrong. Simply by writing 5 to 6 lines in a page, he published the papers. Like that, he has published more than 1,000 papers. Last year only he got retirement. Now some people working in that field are very happy. Now, so we didn't have Shanikata. Okay. So, yakandre avanu retired aada andre eno onthara avaru kelurige. But even though one month back, again I have received one comment from him and I have given the answer. He was wrong and myself right. Okay. I have given the proof also. Right. That was accepted. See here, for that author, XYZ author, Reynolds number is obtained like this. Actually, X should not be there. Please observe that X should not be there. If you are going to use appropriate similarity transformation, then sure you can't find X anywhere. You can't find X anywhere, it will be cancelled throughout the equation. If you are not going to choose the appropriate similarity transformation, then sure you have local variable in your problems. So here you can see local variable, Grashof number and also lambda, some constant. So units, so I substituted the units in that equation. Reynolds number is non-dimensional because I got one, no problem with Reynolds number. See here, Grashof number as well as this one. So next, okay. See here, in Grashof number, the dimension remains per meter cube. But in previous slide, we observed that the dimension of Grashof number is 1, means there will be no dimension. But for his paper, he got this as a Grashof number, and the dimension is per meter cube, means Grashof number is wrong. That's why entire results must be wrong. Similarly, so lambda also contains, so per meter cube as a dimension. Lambda is constant, means it should not have any dimension, but it contains dimension. So that's why by writing these two comments, he has published the paper. Similarly, for another author, so this is also one of the author did the result, obtained the results, and he has published the paper in very reputed journal. There you can observe that Reynolds number, REX, REY. So here you will see REX's dimension is 1, but whereas REY, the dimension is per meter, and then, so delta also, it contains kg per Kelvin into second square, second cube. This means that, so his claim is they are non-dimensional, but his claim is wrong because those constants have the dimension. By writing simply these kinds of comments, so he used to publish the paper. Similarly, one more author, again you can find, the dimensions in the non-dimensional numbers, they should not appear. Similarly, here will be in Brickman number as well as in Prandtl number, you can find the dimensions. That's why they are all wrong results. That's why my intention is, please, before going to do any research work, any problem, first you should verify the equations for the dimension. Then go for the calculation. After doing the calculation, again verify your non-dimensional numbers, your obtained non-dimensional numbers like any Reynolds number, Prandtl number, Brickman, whatever the number, then again verify those numbers for the non-dimensional analysis. If they are non-dimensional one, then there will be absolutely no problem. If it contains some dimension, then again you have to do the calculation. But the thing, so these kinds of non-dimensional numbers obtained due to the choice of inappropriate similarity transformations. Because similarity transformation, you know, each individual equation has its own similarity transformation. Means you are following some researcher, you have taken one research problem, you modified something, means you added some parameters to that problem, but what you are doing, again for the modified problem, you are going to take the same similarity transformation what he has already used. By using those similarity transformation, you are doing calculation, that's why you are going to get local numbers. But each modification leads to the change in the similarity transformation. It means for your own formulated problem, you have to derive your own similarity transformation, then there will be no question of local number, and absolutely there will be no question of dimensions in the non-dimensional numbers. Okay, so this is my, my intention is to give some awareness towards these things. So dimensional analysis. For this opportunity, I am much thankful to, once again, Professor Shiraj Shetty and all other faculty members of this department. By this, actually, I had not a plan to come over here because of Professor Shiraj Shetty. He called me by night. No, you have to come tomorrow. Like that. That's why. So by leaving in the early morning, I come here. Thank you for your love and affection, sir, and thank you for your patience listening. Thank you. If you have any questions, please free to ask. ನೋಡಿ, ಯಾವುದೇ ಕಾರಣಕ್ಕೂ ಆಸ್ಟೋರಾಗೆ ದಾರಿ ಮಾಡಿಕೊಡ್ಬೇಡಿ. ಯಾರು ಫ್ಲೂಯಿಡ್ ಮೆಕ್ಯಾನಿಕ್ಸಲ್ಲಿ ಮಾಡ್ತಿದ್ದೀರಾ, ಅವ ಬರೀ 2 ಲೈನ್ 3 ಲೈನ್ ಬರೆದು he has published more than 1,000 papers. ನಾವು ಕಷ್ಟ ಬಿದ್ದು ಎಲ್ಲ ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಮಾಡಿ ಪೇಪರ್ ಮಾಡೋದು, ಅವನಿಗೆ ಪೇಪರ್ ಬರಲಿಕ್ಕೆ ಅವಕಾಶ ಮಾಡಿಕೊಡೋದು, ಆ ಥರ ಆಗಿದೆ ನಮ್ಗೆ. ಹಾಗಾಗಿ ಇದು ಇಟ್ ವಿಲ್ ಟೇಕ್ half an hour, 1 hour time. That's it. Not more than that, half an hour or 1 hour. That's why take an half an hour or 1 hour. ನೀವು ದಿನಗಟ್ಟಲೆ ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಮಾಡಿರ್ತೀರಿ, ಅಷ್ಟೆಲ್ಲ ಮಾಡಿರ್ತೀರಿ, 1 ಗಂಟೆ ಎಕ್ಸ್ಟ್ರಾ ನಿಮಗೆ ಸ್ಪೆಂಡ್ ಮಾಡೋಕ್ಕಾಗಲ್ವಾ? 1 ಗಂಟೆ ಎಕ್ಸ್ಟ್ರಾ ಸ್ಪೆಂಡ್ ಮಾಡಿಬಿಟ್ಟು ಅದನ್ನು ಡೈಮೆನ್ಷನ್ ಅನಾಲಿಸಿಸ್ನ ನೋಡಿ, ದೆನ್ ನಿಮ್ಮ ಪೇಪರ್ ಏನಾಗುತ್ತೆ, ಪರ್ಫೆಕ್ಟ್ ಆಗುತ್ತೆ. ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು.
Thank you, Girisha sir, for your valuable words and sharing and how to solve the problems in differential equations. Now I request all the dignitaries to felicitate Girisha sir.
Good morning to everyone. Today I will explain a new very important concept, that is data science. Nowadays it is very demand in mathematics because it includes data and mathematical modeling. So we use the mathematical modeling and some equations how to model it, because I had 10 patents in this one and awarded 4 PhD students. So coming to the next, this is my abstract. And what is data science? Data science means what? Data science means nothing but it is a multidisciplinary approach. Here we can extract the actionable insight from the data. Means data science, why we call it is as a science? Data science combines multiple fields including statistics, scientific method, artificial intelligence, data analysis, computer science and business knowledge. Because why it is important? Because data science, why the science name has to be given to this one? Because science means it is a well-defined results. If you do some experiments in lab, if you noting the data, if you do the same experiment, so again you will get the same result. So previously whatever the scientist has discovered, Newton first law, second law, third law, now also it is still valid because science will give a particular result and it is valid for all time. So that's why data science means science includes a particular results. So that's why we are using this science. Consider some decision making. Consider that one company is there. Example, take Maruti making company. So the company owner comes to the data scientist and he will ask and he will tell that next year I want to launch a how many car in the market, so you tell me. So now the job is for the data scientist, he has to give some figure. So boss will ask, you tell me how many cars we have to manufacture. So for that he will ask the boss, data scientist will ask the boss, give me the data of production of car, historical data, competitor data and marketing data. So most important analysis is that taking the data and analyzing and finding the actionable insights and useful insights of the result and making a decision. So this is a very important topic because nowadays how we are using our data and mathematical concepts using mathematical modeling and we are getting the profit. So life cycle of data science is that the data science process is very simple to understand and involve the following steps. So this is the 6 important steps in which a data science or any data scientist will use it. First step is that business understanding, second is data collection, third is data preparation, fourth is exploratory data, fifth is model building and sixth is model deployment and maintenance. So business understanding. So here the important is that a data scientist has the knowledge, he has to have knowledge of what is business they are going, because without the business knowledge it is very difficult. Next, data collections. So how the data they are collecting, from which source they are collecting. They are collecting from authority source or any fake source, because if they collect fake source means there is no use, because after building a model and deployment of the model. So the source is very important. After that, downloading the data preparation, how to prepare the data. Next, coming to the exploratory, fourth step is exploratory data analysis. Fifth step is model building and sixth step is model deployment and maintenance. I will take some simple example so you can understand with this using this model. So whatever the data they have collected, it is in this form, it is in digit form. So they have collected from a reasonable source or cloud computing or whatever it may be. It is in this form, and there are some attributes of short form of NP, REG, glucose, BP, skin. So after that, data scientist will give a job to data analyst for data preparation. Second step, we have to convert that random data into a perfect one Excel sheet. For this, we use the Python coding and we use some data sheets, Excel formula. After that, data preparation is very important. So some missing value will be there. So we have to correct the missing value. After data preparation, we will delete some missing values. After that, after that we will do exploratory data analysis. First we load the data into the analytical sandbox, and after that we come into the mathematical equations, that is dependent variable and independent variable. Now this data had a shape. Now we can understand what type of relation there is a dependent and independent variable way between the so many equations. And this is the model building. I have taken 3 decisions. So if example the glucose, if it is less than 127, what will be the value, and it is greater than 127, what will be the value. So after model building, we will model deployment and maintenance. After that, the work of the data analysis is responsible. So the time is very less. I will finish so fast. So after decision making, I will give you some logical importance of the algorithm, how the algorithm will be written. That is very useful. Find the largest number among the numbers. Like example, you have to write an algorithm, find the largest number among this one, like A, B, C. So how you have to write? Before writing any programming, you have to write your algorithm with a logical thinking. Next is start, read the 3 numbers to be compared as A, B and C. Check if A is greater than B. If 3.1 is 2, then check if A is greater than C. So that T.4, next to 4 is point. After that we have to draw a flow chart which is common to every computer student and mathematics students. After that we will write a Python programming. So this is my YouTube channel. If you want this, you can scan it, because I am having in so many community. If you have any opportunity, because free coaching of IAS, free coaching anything, I will update here. This is my YouTube channel. Here I am giving some detailed videos in 2 languages. One is English language and other one is Hindi language. If you want a new research completely, if you can see my videos, then you can understand clearly. So please go to Google Scanner and scan it and subscribe my channel. Then you will getting the notification, and day by day you will get the update, because I have started a research course subject, that is data analysis, that is data science, which is the backbone and main core of mathematics. Because if you know the mathematics, then only we can model the models, because mathematical model plays an important role. So hello students, please scan it. My request is take this Google screenshot and scan it. Okay. Thank you very much. Any questions? If you have, you please ask me. Any questions? Sir, much bit sir, first. Vijay. Bye.
ಏನು ಬಂದ್ ಮಾಡಿ Any questions from the audience? Vatsala, any questions? Is there no questions? Sir, thank you very much for accepting our invitation. You are coming over here in your busy schedule, accepting our invitation and grace this occasion grand success wholeheartedly. Thank you very much, sir. And next time also you come. So all of you give him a big hand.
Sir is like my big brother, because in my Viva, sir came as an expert. For my good luck, as my Viva completed, within shortly I have got appointed in Central University. With blessing of my brother, sir has given me a very good Ashirwada, we can say. Thank you so much, sir. No, sir.
Sir is working in very prestigious Central University. Immediately we are appointed and he is doing very good job.
for 3 days international conference. Uh, I would like to introduce Dr. T. Palaniswamy sir to the participant gathered over here online and offline. Dr. T. Palaniswamy sir joined Department of Mathematics, Amrita Institute of Technology, Coimbatore in 2026. Presently, he is professor in Department of Mathematics, School of Physical Sciences, Amritnagar, Coimbatore. He obtained his doctoral degree from Amrita Vishwavidyalaya, Coimbatore. His area of research is the estimation of variance function in beta-elastic regression models. Interest of Sir also includes regression analysis, signal processing and image processing using wavelet techniques and space representation theory. Sir has delivered number of lectures in FDP, workshop, seminars, conference and all national and international events. He has organized an international conference on applications of fractal and wavelets in January 2015. Sir have more than 20 years of teaching and research experience. A lot of students have completed their master's thesis and some of them are in foreign and at all over the world at good positions in university and in research centers. Once again I welcome Dr. T. Palaniswamy sir for this invited talk from Karnataka University, Dharwad. Welcome sir, and the session is, the chair or the handle is towards you. Thank you sir, welcome.
Thank you. Thank you so much for your nice introduction. I once again thank the Professor Sirala Setti for giving me to give a presentation in this nice occasion. So just a minute, I'll check my presentation. My screen is shared. Tell me, are you able to visualize my screen?
So please share the screen.
When I'm sharing, I have a small problem. I'm not getting it actually. Just a minute. Share screen.
Third option, sir.
Third option. This one, Mahesh Setsi, right? Meet needs permission to screen share, okay.
Sir, at the bottom there is a microphone symbol, then towards right video call, and the third one is the screen sharing option.
Yeah, there is an arrow mark that when I am trying.
Okay, sir. Yes, sir.
Vatsala, is it okay to see? Is my screen visible?
Yes, sir.
Okay, thank you. Well, my talk today, when I compare to the whole of the sequence of speakers seems to be a bit different. This is connected to statistics, much of it. When I have gone through the set of speakers who are going to deliver talks in this conference, there are a lot of people on various other domains, but I could see some of the people who are connected to data science. And this, of course, regression is also connected to data science, but initially my work was regression analysis using wavelets. I slightly started to move to different areas of regression. Now the presentation of today, my talk will be on regression model specifically for interval data. So that's a very recent work that have been attempted by people in the statistics domain. Regression has been there for a long since, but the regression for interval data has become interesting and much required topic for people who are working in data science, and it's much required in industry, and that has become possible because of the computational facilities that are available right now. So now the abstract of my work will be this. The work will be proposing and estimating the parameters of a polynomial regression model. A regression model, particularly polynomial regression model. This, of course, is involving some sort of linear regression model principle when both the independent and dependent variables are interval value. We are considering variables involved in our regression model will be intervals. We define the regression model using the interval arithmetic. There is a new idea, of course, that's been used by people in various domains. Arithmetics in interval. How do we add intervals? How do we subtract? How do we multiply? How do we divide? All those things are required for various purposes. We are going to use that interval arithmetic idea for our regression analysis, connecting data involving intervals. So particularly this work is going to involve product of intervals that has never been attempted so far by people who are working in the regression model connected to interval. The proposed model is involving the mid component of the interval x square. So when x is a variable, that doesn't matter, x square is very simple to compute, but when x is an interval, the square of the interval, x square, how we are going to compute that requires the interval arithmetic. Now in our work, we are going to consider the square of the interval just by considering the mid value of the interval alone, not by considering the spread of the interval. That's the different kind of attempt we are trying to make. The presence of the spread components of the intervals will lead to the estimation of the parameters of the model by using constrained optimization. So normally for interval estimation or for regression estimation, statisticians used the least square principle, but here we are going to use quadratic constrained optimization, I can say now. Let me introduce what it is going to be. Then we employ quadratic programming to optimize this constrained least square estimation. That will be our attempt in this particular work. So now let me tell you why the interval value data have become so crucial for us at this juncture of time. So plenty of real-time phenomena results in data that are random and are essentially interval valued. So you can say randomness is quite obvious to understand for anybody. You cannot expect every time that the value that I am expecting is going to come out of my experiment. What value we'll be getting out of our experiment, we cannot predict, therefore that will be most of the time random. And that doesn't have much surprise, but the interval value data, where it is coming from and why we are very specific about interval value data, particularly that interval is also random interval. That's quite interesting. That's what is the motivation for this particular work. The data may be interval because of imprecise nature or to hide the exact value of the variable of confidentiality reasons. Maybe that cyber security people may be requiring it just to hide the particular value that I want to tell in an interval in a particular fashion or in particular fashion, or we may be using interval for various other situations also. We'll be talking about that later. The mathematical economics that may requiring interval value data, maybe that bandwidth of particular economic status may be used many times, and systems and control, statistics and error and numerical analysis involve intervals suppose when you are studying error, confidence interval will be using in most of the cases. That is also a kind of interval data. That is often studied by various researchers for various purposes. The practical problems of interval data arise in petroleum industry in the form of inequalities. I am not very sure what kind of interval they are going to use, but when I have gone through the literature, I could understand that petroleum industry is using this interval data for their problem, and daily fluctuations of stock price. That's quite obvious to understand. Minimum and maximum value of a particular stock through the day, if you take, it's going to be an interval. What would be the minimum value and what may be the maximum value, and the fluctuations should have happened in between. And temperatures, of course, minimum and maximum temperature, therefore all in between temperatures also will be considered for our study. And blood pressures and so on. Suppose you take blood pressure of a particular person through the day, there will be some minimum value, there will be some higher maximum value. Those two values will be forming an interval within which all the fluctuations of the blood pressure should have happened for a particular person. Now, all these things are fine. Interval data are existing very much right from the beginning of our study. But now, due to the explosive growth in the use of databases and the advent of computers, that's the important point that I have to understand. If computers are not available, then I don't know whether people can attempt to go for regression analysis on interval data. Interval analysis has got an impetus for quest in numerical computation formations. Therefore, it's all because of the computational facilities that are available. Now we are able to attempt any problem, particularly this problem as well. Now, related to this particular talk, two basic things I just feel that are quite essential. One is regression. We have to know a little bit about what is the basic of regression, because when I have seen the sequence of speakers, all those talks are mostly about the fluid dynamics or pure mathematics and that kind of things. Maybe wavelets are also wavelets are also part of the presentations of many of the speakers, many of the professors. But as it is a completely strange topic that I could understand when I have gone through all the set of talks, I just take little time to introduce what actually I mean by regression, because the young researchers also would have come mostly from this part of the mathematics and the mathematical sciences, but this is a bit different. Therefore, let me introduce a little bit about regression, what it is, so that it will be comfortable for you to proceed. And let me talk little about interval arithmetic, how I am going to use that interval arithmetic for the problem of regression analysis connected to interval value data. Now, history of regression goes like this. In addition to the history, etc., I will be telling you a little bit about how the regression can be understood easily. So, Galton is the founder for actually the regression analysis to start with. Actually, there is an idea like correlation and regression, many of you might be knowing, and that was associated, that was actually initiated, that idea, that study was initiated by Galton. He published a paper in which he has used first time the word regression that tells you how you can see Anthropological Institute of Great Britain and Ireland, in that journal he has published an article, Regression Towards Mediocrity in Hereditary Stature. That was just by considering the heights of the hairs, how that goes. That's what they have first time used to study regression. That was called to be regressing. An important tool of regression study, the method of least squares. Whenever we study regression analysis, whenever we do regression analysis, immediately the tool that we'll be thinking of is least square method. What actually least square method, that will also we'll see. Therefore, it's not completely Galton. He has only introduced what is regression, but how we can work with regression was because of the idea of least square, which was completely tried by Legendre and of course Gauss. It was all in 1805 and 17, not very long back. Now, why this regression analysis is significant? Let me tell you a little bit more theoretically, but I will tell you by an example as well. Regression analysis is a statistical tool for the investigation of relationship between variables. When I deal with two variables, naturally in mathematics also will be interested in knowing what will be the relationship between them. Whether it is a line or a parabola or a cubic curve, or it is some other function like connecting x and y, or the trigonometric functions like sine, cos, secant function, or its exponential function or ln function. So all such relationship is always interesting for you when there are two variables which are connected. That is mathematical relationship. But when it comes to regression analysis, it is not mathematical relationship. We are going to bother about statistical relationship. Where I mean the statistical relationship, there will be some sort of randomness involved both in the variables x and y. X is not a deterministic variable, y is also not a deterministic variable. They are actually random variables. In such a situation, if you want to study the relationship between them, then the regression analysis is coming. There is quite a lot of difference between trying to understand the relationship between mathematical variables and statistical variables. This involves a different technique, whereas mathematical analysis or mathematical relationship can be studied a bit easier. So you can recall whenever we do something in mathematics, we'll be always using the word assume. The assumption is completely foregone when it comes to problems of statistics. That means we'll be letting the natural thing happens. We don't want to suppress anything just for the sake of doing the mathematics behind that. Let me see that the actual situation is completely playing. That means there will be some sort which I cannot control, which I call as randomness. When randomness is involving in the variables, then now I can study the relationship between them is what we'll be doing in regression analysis. Simply for an example, let me take, there are some n number of places in which number of rainfalls are n different values. Let me take throughout the South India. The number of places I am considering is n. In all n places, what I am doing, or I will be considering n different amount of rainfalls. They would have happened, every particular amount of rainfall would have happened in some k number of places, or n1 or first value of the first amount of rainfall, there may be k1 number of places. Second amount of rainfall, there may be k2 number of places. Similarly, there are nth different amount of rainfall may have kn number of places in which that particular amount of rainfall would have happened. Then what I do, I'll just study the amount of paddy cultivated in every different set of places in which the amount of rainfall was the same. Suppose I take the first amount of rainfall is some particular amount of rainfall, let's consider. In all those places in which that amount of rainfall is registered, you can just go for studying what will be the amount of paddy cultivated. You can see the amount of paddy cultivated despite the amount of rainfall is the same, need not be same, it will be different. Similarly, in all different set of places in which the amount of rainfall was the same, the amount of paddy cultivated need not be the same. Then what I do, I want to take the average amount of paddy cultivated in all the places where the amount of rainfall is the same. So if I have n values of amount of rainfall, in which I have n sets of places in which the amount of rainfall is the same, then I will be taking all those places what is the amount of paddy cultivated, then I will take average amount of paddy cultivated in each set. So now what I have is, I have the amount of rainfall n number and corresponding n averages of amount of paddy cultivated in n sets of places. So now I will try to study the relationship between amount of rainfall and the average amount of paddy cultivated. That is coming under regression analysis. Why it is coming under regression analysis is because when I take the amount of paddy cultivated, it is involving randomness. There are multiple places in which amount of paddy cultivated are different. Then instead of taking every individual places where the amount of paddy cultivated are different in spite of the amount of rainfall is the same, I will be considering average amount. I don't take every individual values to connect it to the amount of rainfall, but I will be connecting the average amount of paddy cultivated to the amount of rainfall. So that relationship I study, that will be coming into regression analysis as it involves randomness. So why we are going for regression analysis, or what is the concept behind regression analysis, is to reduce the amount of error. When I try to find this relationship between this sort of x and y, naturally I cannot have a perfect relationship identified because perfect relationship won't exist, but I'll be going by some technique to see that the error that I'm getting when I'm estimating or when I'm not determining like mathematics, when I'm estimating by using statistics, error cannot be avoided, error is inevitable, but my idea is, my goal is to see that the errors should be minimized. How can we proceed further? That's what is the total work behind regression analysis. Now, the practical importance for regression analysis is this. A conclusion on underlying mechanism generating the data. Let me have a data like I told you, that the amount of rainfall in few places and the amount of paddy cultivated. By considering it, I can see how I can connect them. So this data that I am having is having the amount of rainfall and amount of paddy cultivated. There is some mechanism that has generated this data. That means the paddy cultivation is the mechanism that has generated this data, amount of rainfall and amount of paddy cultivated, and I will see how I can get the, how I can learn the underlying mechanism. And then to control the accuracy of the measurements that may decrease during the course of time because of the loss of precision by the devices used. When I proceed, so this will be used to predict. Regression is mostly required for predicting what's going to happen the next occasion, or what's going to happen for a different X value. That's what is the total idea behind it. That's the practical importance of regression. Therefore, most of the time, regression will be used for prediction. So data science people are currently working many of the problems based on regression only. Different kind of regressions have come, but the statistics people are talking about still the basic regression study that we have done, but lot of new regression techniques have come by using measures. That is a different problem to be explored. Let's not go into that, but let me come to our problem of regression connecting to interval value data. Now, when it comes to regression, there are two things. One is parametric, another one is non-parametric. So what do you understand as parametric regression and what do you understand as non-parametric regression? I can put you this way. When I just show you the kind of data, this is the kind of data that I'm having after observing a particular set of variable X and Y. Here they have given like hydrocarbon level and oxygen purity. So when I plot it, it looks like this. So it's quite obvious that there is no particular curve that I can assume, which is quite familiar to us, which will pass through all the points. But it's quite obvious when I look at it from a faraway place, it will be mostly around a line. Therefore, what I try to do is now, assuming that the actual relationship between this X and Y is a line, I'll be trying to fit the line. But if I fit the line, can I expect that line should pass through all the points? No, it will never. That's what we are calling as error, that we'll see it later. So this is what is the situation between a line in mathematics and a line in statistics. So here, line is my guess. How I am guessing that line should be the connection between X and Y? Just by observing the data, there may be different possible curves that I can take, which can be an nth degree polynomial if there are n plus 1 data. But let me assume that line may be easier for me to work with. Therefore, I perceive just by looking at this data, line may be a suitable fit for the data. Then, when I'm fitting that using a line, then it will be something like y equal to beta naught plus beta 1x. Okay, line I could understand. Yes, by looking at this data, it looks like there is a pattern of line. When I understand that equation of the line must be something like y equal to beta naught plus beta 1x, then that beta naught and beta 1 is what is my interest. I have to understand what should be that beta naught beta 1 which will be connecting this set of X and Y. So I have to find that parameters. So we'll be calling the beta naught and beta 1 which will be the coefficient of X and the intercept as the parameter of our regression analysis. This is the simplest problem that I am talking about. It need not be always one variable. There may be multiple X, X1, X2, etc., Xk, which may be connected to Y. In that case, there will be like equation Y equal to beta naught plus beta 1 X1 plus beta 2 X2, etc., etc., plus beta Xk. Therefore, there will be K plus 1 variables. All those K plus 1 parameters, I can say that K plus 1 parameters are to be estimated. That's what we are calling as a parameter. So that is why whenever your data looks like this and it's possible for you to guess that line must be the right fit for this particular one variable, one regressor and one response, then that beta naught and beta 1 is our interest. Once I get it, then I can understand, though all the X, Y are not lying on the line, I can find a line that will be very close to all these points. Using that, for any new x, I can get my y. That's what is the prediction I told you earlier. Therefore, this is what we are calling as parametric regression because it involves parameters beta naught and beta 1. So that's what we are telling now. Parametric regression model is classified in broad sense as the parametric model when we assume that mean response has some pre-specified function form. Pre-specified function form here is a line. That's what I am telling, pre-specified function form. That example that we took was a line. It need not be line, it may be a parabola, or it may be cubic or whatever it is, or it may be with multiple variables, then it will be plane if it is two regressors and one response. Various different possibilities you can think, but all of them can be considered to be models which are involving some parameters. That parameter will be of our interest, that is what we want to estimate. So such models we will be calling as parametric model. And there are some other situations where the points need not be looking like this. It will be some other kind of unknown structure where I can just try to get the curve that will be closer to all the points. I cannot say it's a line, I cannot say it's a parabola, I cannot say anything that is known to me. I'll be trying to fit a curve to that. If that is the kind of situation we'll be dealing with, then that is what we are calling as non-parametric regression model. That's what you can see, that a model is classified as non-parametric regression model when there is no reference to a specific form of the mean response. I cannot say it's a line or parabola or cubic curve. It will be some sort of connection between x and y that we want to understand. That will be non-parametric model. Then now parametric non-parametric model can be understood a little more better at this way. Non-parametric modeling of regression model is always good because we are not restricting the assumption. You can just let the data go as it is, and you want to find the relationship between x and y as it goes. But when you are putting an assumption like, oh, by looking at the data I could understand there must be a line connecting this x and y, then we are suppressing something. We are not letting the nature to go as it is. So that's what we are calling as parametric models. But parametric model is always easier because Taylor series and all will be useful for you to reduce any problem to linear problem or something else. That sort of mathematics is coming behind, which will be converting any problem of any degree of your variables can be reduced to first degree or linear model. It can be studied easy. For that purpose, we'll be going for all such regression linear parametric models. But even then, they are putting a restriction on that. That's what we are telling Procrustean bed. That means a bed is already made, so you have to lie accordingly. But it's not the right thing to be done. But anyway, we'll be doing most of the time that linear regression model and regression model which is involving some parameters. Fine. The result of non-parametric regression analysis is a curve fitted to the given set of data. We don't bother about what is the equation connecting x and y, but we'll be getting a curve. That's what non-parametric regression model all about. Now we have seen this already. Now this is what is behind your least square principle. You can see now all the dots that are shown are the data. So x1, y1, x2, y2, x3, y3, they are plotted. When I plotted, I could see this is how it looks like. But just by looking at the data, I could understand that I cannot, rather than thinking some curve which will be passing through all the points, it is very reasonable to assume that there may be a line which will be very close to all the points after plotting it. That's what is the parametric model we are talking about. Parametric model will always help you in seeing that your complexity of the work will be reduced, and it will be simple in many of the cases to just go ahead with your prediction, and you will not be losing much of the information also. In such cases, you can go for parametric model, and the linear model is one among that parametric model. Now, what is our ultimate aim? It's easy to understand. There is a deviation between the actual point and the line. So all those deviations you consider. Now what I want to see, all those deviations are less. So is it simple for me to reduce all the deviations? It's not that simple, because there are some positive deviations and some negative deviations. I cannot take all deviations individually and study. That's quite difficult. Sometimes some illusion also, or some wrong conclusion may also be possible. by taking all the total deviations, I can see some positive deviations, some negative deviations. When I add together, that may become zero deviation, but it is not right. Actually, deviations are there. Some are positive, some are negative. But when I add it as it is, it will give me zero deviation. It's not right. Therefore, what I do, I have to go for squaring of the deviations and I'll be adding it. Instead of adding the deviations as it is, I'll be squaring the deviations and add it. And square of the deviations should be minimized. That's what we are calling as least square principle. I want to minimize the sum of the squares of the deviation, which is what we are calling as least square principle. That's what we have seen in the earlier slides, which is very essential when you want to do problems connected to regression analysis, particularly parametric regression. Now, all about basics of regression, hope must be okay for all of you. Now we'll proceed further to interval arithmetic. Why? Because our ultimate aim is to talk about regression for interval value data. It's not about regression for just real numbers. It's about intervals. I have one input interval, I have one output interval. I want to connect those two intervals by means of some relationship. Hope this should be okay for all of you. If any questions, I'll wait. Problem now is to see, instead of connecting one X and one Y, like the amount of rainfall and amount of paddy cultivated, here I am taking one interval as my X, another interval as my Y. Now those two intervals must be connected some means of functions, where these intervals are actually random intervals. So I have to get the relationship between these two intervals. When I start my problem, I will have many different input intervals and the corresponding output. Say for example, I have n number of input intervals, say x1, x2, etc., xn, and all x1, x2, xn are all not real numbers, they are all intervals. Corresponding to them, I will have output intervals, say y1, y2, y2. Say for example, I can just modify my example like this. Instead of taking a specific amount of rainfall, I will be taking amount of rainfall lying between this and this. Say 10 centimeter to or 10 millimeter to 20 millimeter, or 0 to 3 millimeter. There are multiple places in which the amount of rainfall may be 1 millimeter or 2 millimeter or whatever. They all will be clubbed into that particular interval, and in which I will be finding all those places in which the amount of paddy cultivated will also form an interval. The amount of paddy cultivated may be, say, in 1 hectare, it may be from 4,000 quintal to, or 300 quintal to 500 quintal. So different amount of rainfalls which will be easily understood as intervals, and in all the sets of places in which the amount of rainfall falls in this interval, there will be different sets of paddy cultivated. Now by taking this data, I want to see what may be the relationship between the amount of rainfall and the amount of paddy cultivated by means of considering them as intervals. This is what is the problem we are going to deal with. So there are multiple real-time situations you can think of. I will leave it to you, but let's proceed. As we go at the end of our presentation, we'll have a particular real-time example that will also be very interesting to understand and to analyze. Now, before going to that, let me talk a little about how do we do the arithmetics in interval. Now suppose if A and B are same in an interval, where I am considering the interval to be A comma B, I stands for interval here. When A and B are same, the interval will be degenerated. It will become a single point. That's not our interest. Now suppose I have to add two intervals. That's what given here. You can see A plus B, A comma B and C comma D. I am adding two intervals, which is not quite familiar, or which is not necessarily a routine affair for us. We'll be always adding real numbers, complex numbers, etc., etc. But it's an interval. Of course, interval can be considered something like complex numbers. Then A comma B can be taken to be like A plus IB. I'm just telling for you to understand. And C comma D, or otherwise vectors. Linear algebra, we would have done a lot of times. How do we add two vectors? The same thing is what addition here as far as the interval is concerned. I'm adding the lower limit of the interval to lower limit A plus C, and upper limit of the interval to upper limit. Otherwise, infimum and supremum we can say otherwise. Infimums are added to form the infimum of the new interval. Supremums are added to get the supremum of the new interval. Then multiplication is what is the technique that is not much popularly used for various works. That's what is the new attempt that we are doing. Of course, the multiplication of it is also defined for certain problems in various other domains. So we are borrowing that multiplication idea for our problem of polynomial regression study connected to interval value data. So when you take two intervals to be multiplied, it's really brainstorming, and it's not easy to catch just by looking at two intervals how we are going to multiply. Addition, of course, is little triggering us to think we are adding like two component vector, or we are adding like a complex number. It's not so, it's entirely different. I'm multiplying a comma b and c comma d, it will be this. Of course, you can think of complex numbers multiplication. Maybe it's something of that sort. Minimum of, you are taking a with c and a with d, b with c and b with d. So multiplying all the four values involved in two intervals. So you take all combinations, multiply. Out of that, which will be the minimum? That will be the lower limit of the new interval that will be formed, which will be the result of the multiplication. And you take again all four combinations of product, out of which pair is giving the maximum value, that will become the upper limit of the interval. So lower limit will be the minimum of the products of all the four values, and upper limit will be the maximum of the product of all the four values. That's how we'll be defining our product of intervals for our problem. Of course, it has been used for various other problems. Therefore, we are easily borrowing from the domain of mathematics where they are using all such things. Therefore, there is no botheration about that as far as interval valued regression is concerned. Now, we'll be taking some other understanding of interval. You can just listen to it very carefully. The parameters mid-I and spread-I can be used to represent every interval I belonging to the script I, which I am calling as the collection of all intervals. So I am taking one interval I. That interval I can be written to be mid-I minus or plus spread-I. You try to understand what is the meaning of that. I can write in the very next line what is mid-I. Mid-I will be supremum of I plus infimum of I by 2, which means just the midpoint of the interval I am saying, which is what I am calling as mid-I. And spread-I will be the difference between the maximum and minimum divided by 2. So suppose if it is 2 to 5, then I will be taking 3 by 2 as the spread-I. And 2 to 5, 7 by 2 will be my mid-value. Then what do? You will go for mid-I minus spread-I. You can see mid-I minus spread-I will be supremum I plus infimum I by 2 minus supremum I minus of supremum I minus infimum of I by 2. Then when I do that, supremum will get cancelled, infimum will become doubled. So 2 times of infimum of I by 2, which is infimum of I, which will be the lower limit of the interval. Similarly, mid-I plus spread-I will give you simply supremum I 2 times divided by 2, which will become supremum. That means the interval is from lower limit to upper limit. Therefore, the interval can be represented differently like this. It's not any new algorithm. We are just representing the given interval like this. 2 to 5 I can write like, one is 7 by 2, that is mid value. Another one is the difference. Difference means highest minus lowest. 5 minus 2, 3 by 2. So I will be taking these two. If it is, if it is 2 to 5 is the actual interval, then 7 by 2 is the mid-I, and 3 by 2 will be the spread-I. I am taking those values to get my interval represented. In the above expression, mid-I, supremum I, infimum I, spread-I represent the mid, supremum, infimum and spread of interval respectively. Now, for our problem of least square principle we have used in simple regression model, we are trying to bring something similar to that. That will be this particular distance measure. And when I want to find the distance between two intervals, you can just imagine you are taking intervals, say considering it as 2 component vector. If you plot it in a plane where I have 2, 3 and say 4, 7, it's something like 2, 3 and 4, 7 vectors in 2-dimensional plane. Then you can just try to find the distance between them. So how do you find the distance between them? That's what, so it's going to be something like a rectangle, and we are finding the difference between the points inside the rectangle, something similar to that we'll be attempting. That will be given by this definition. mid A minus mid B whole square. I'm taking mid values alone. I'm taking the difference and squaring it. It's like x1 minus x2 whole square, yn minus y2 whole square, mid and spread. So mid becomes one component, spread becomes another component. And we'll be giving some weightage for spread. So if I am taking mid to be 1, then spread I'll be giving weightage theta. So which is important for me. Suppose I give theta to be 4, then I'll be giving more weightage per spread. If I'm taking theta to be value that's lesser than 1, it will be even lesser importance when we compare to the mid values. That's what is the distance measure that we are introducing for the purpose of least square connected to the estimation of parameters in interval valued regression. Right. Now, you can just see that mid I minus r plus spread I we have already seen in the previous slide. I'm just putting that in a different format now. Mid I into 1 minus r plus 0 plus spread I into 0 minus r plus 1. Then you can just multiply mid I inside. 1 minus r plus 0 means both are 1. Then it will be mid I comma mid I. The next one is spread I, 0 minus 1 and plus 1 will become minus spread I and plus spread I. So when you add mid I minus spread I and mid I plus spread I, that's what the actual interval. This is another way of writing any interval. Okay, let's come to now definition of random. In fact, random variable as the complete the domain of the conference is something connected to different domains of mathematics. As we are talking a little bit about statistics, let me introduce the small basics of that. Random variable will always be a function that will be connecting all the possible outcomes that you have in your set to a real number. That's what we are calling as random variable. Here it's not random variable, it's a real, it's a random interval. So random interval has to do what? Suppose say for example you are tossing a coin, you'll be getting a head or a tail. The head will be connected to 1 if you are taking the definition of the random variable to be number of heads you are getting. Number of heads you are getting when you are getting a tail will be 0. 1 or 0 will be the random variable value. Here instead of taking that 1 or 0 as the real numbers, we'll be taking them to be intervals. You can take some example in which this will be really required. So I am considering all the possible outcomes of a random experiment. I cannot say this is the outcome I will be getting when I am doing the experiment, but I can tell you these are all the possible outcomes. By considering all the possible outcomes, then I will be connecting every different possible outcome to certain interval instead of a real number. That's what we are defining as random interval. Hope you can understand what is the meaning of random interval now. Instead of connecting the outcomes to a real number, we are going to connect outcomes to a interval. That's what we are calling as random interval. I'll skip it. Now, let's go to our work now related to our regression for interval value data. So there are works, simple linear model on the mid components of random intervals to different models involving the mid and spread components of the intervals. Those are all the literatures I have collected for this purpose. And few of the models involving mid and spread components of the intervals used to different models for mid and spread. Earlier on what I was telling is, your output is mid only. Mid of the output alone is what is your interest. You are not bothering about the spread. In such cases, that mid can be estimated by using the mid and spread of the input. Mid and spread of the input can be used to predict the mid of the output. I am not bothering about the spread of the output. That will be the first bullet I am talking about. Second one, there are both mid and spread in the cases of input and output. So there are a lot of people, research have happened by considering those two things. Now, also there are combined models of mid and spread components, the same coefficients for both of them and few others the different coefficients. So these are all little minute things you have to watch carefully. Here I will be taking mid and spread with the same coefficients. So I will be giving an interval for which the coefficient is alpha, then mid also will have the same coefficient, spread also will have the same coefficient. But instead, some more problem, I will be writing that interval as that mid into 1 plus or minus 0 and spread into 0 plus or minus 1. Then I will be giving a different coefficient for mid and different coefficient for spread. Then coefficients are different, that will also be possible. Therefore, so many different possible combinations of mid and spread can be considered for the study of regression for interval value data. That's what all the literature are talking about. Anyway, let's not go much deep into that, because if you're interested, you can just some time over all the kind of work that I've done. I'll just skip this now. But none of the earlier efforts, this is what is the motive of the work, considered the square of the interval. All the work that I have done so far are intervals which are involving only x alone, not x square. If x is the input interval. If there are two input intervals, x1 and x2, then they will be considering only your output interval is equal to some alpha into x1, some beta into x2, or alpha 1 into mid of the x1 and beta 1 into spread of the x1 and alpha 2 into mid of the x2 and beta 2 into spread of the x2. That kind of work only have happened, but none of the earlier research have attempted by considering square of the interval. What I am telling is the input-output intervals might be connected sometimes by means of a parabolic kind of relationship if you are talking in terms of the real value. That's what is the purpose of the work. That becomes possible because there are situations in regression connected to real numbers that polynomial regressions are there. So similar regressions might be required in some places where we are studying the relationship between the input and output intervals is my claim. So now let's see. However, in situations of classical regression analysis where the functional relations between response y and the independent variable x cannot be adequately approximated by, so what I am trying to tell is it is not necessary or it is not possible to understand the output y just by considering x alone. It barely requires square of x also to understand the y. If I use such kind of model, then only my prediction will go with least error. If I am not considering square of the input value, I am not talking about interval, when we are doing with real numbers, when I am not using real numbers, I am using only x, my prediction on y may not be having lesser error, it may have more error. If I want to reduce the error on my prediction, then I should naturally include the square of the x values also in some cases. I am not telling it's always, in some situations that is very badly needed. That's what is the existing works on the polynomial regressions as far as real numbers are concerned. My claim now is such a situation will come for intervals also. So therefore, there must be a regression study for interval value data which includes the square of the intervals.
Hello, sir.
So now proposed interval regression, you just see to that. This may again lead to all different possible combinations of mid and spread components of x square along with the mid and spread components of x. You can see I can take mid x and spread x and mid x square and spread x square in some cases, or I can take mid x, spread x and mid x square alone. I don't want spread x square. All such things are possible because spread x square might not be meaningfully contributing for some problems, whereas mid x square may contribute. These are all the guesses that we are making. But the proposed model is considering only about the mid component of x square, but not
excuse me, sir.
Yes, sir.
Sorry to interrupt. We have very less time and some sessions are to be delayed by some 20 or 30 minutes.
Yeah,
so
I
please,
think my time for me is still 1:15, right?
Please wind up in within 5 minutes. That will be very
sure,
good.
Sir, sure. I'll be sticking very much to the time, no doubt. So we propose a new partial polynomial model for a random interval. This model involves mid components of linear and quadratic terms of interval regressions to contribute on the mid components of the. So we are going to consider mid of x, spread of x and mid of x square just to predict mid and spread of the output interval. So mid x and mid x square will be contributing to mid y and spread x alone will be contributing to spread y. That's the kind of regression we are going to study in our problem. Now proposed model, I am just writing this, you just listen to it. Y be a response interval, that's the output. x1, x2, xk are the input intervals. Now I can write my model like you are seeing in the equation. Alpha j into mid of xj into 1 plus or minus 0 plus alpha k plus 1 to mid of xj square and 1 plus or minus 0. and beta j into spread x j 0 plus or minus 1 plus t. You can see here I have not used spread x square. I have used only mid x square and spread x, and there is a random interval d involved in it. Now the coefficients you can see there is alpha connected to mid x and alpha connected to mid x square, beta connected to spread x. These are all the things that you have to note. Now our aim is to see what will be this alpha j's and what will be our beta j's. Remember, spread x cannot have negative value as the coefficient. If spread x coefficient becomes negative, then your interval cannot be a meaningful interval. Your interval will be something like 3 to 2. It will be starting from highest value to lowest value if your the coefficient becomes negative. That should not be the case. Therefore, there is a condition on beta j, it should be always positive. So that is non-negativity condition I am talking about. Therefore, whenever this non-negativity constraint is not there, the estimation of the parameters can be done by using least square principle. But whenever there is a negativity constraint, non-negativity constraint is there, then your least square will not work. The estimation of least square will not go correct. In such situations, we'll be using quadratic programming to estimate beta j's. Therefore, you understand just by looking at the coefficients, alpha j's can be estimated by using least square, whereas beta j cannot be estimated by least square. If you are estimating by using least square, it will go completely wrong. Sometimes it will give you meaningless interval. Therefore, I have to estimate beta j's by using quadratic programming. That's what is the total idea behind our estimation. Now, I'm using that least square principle by using the distance measure we have defined already. That's what is this particular equation I'm writing, d theta square of ya, the distance between ya and the estimated thing. Actual response and the estimated response, they too should have minimum distance is what is our total aim. That gives me these two equations. One is connecting to mid, the first equation, and plus of course the second one, you can just de-link the two equations, one in the first line, another in the second line. First line is all about mid, the second line is all about the spread. Those two equations to be solved separately to get the values of alpha j's and beta j's are estimated. Remember, alpha j's can be estimated by using least square as we are doing in simple regression models, whereas beta j's cannot be estimated by using least square models because that may lead to negative beta j's, which may finally resulting in nonsense intervals, which should not be the case. Now, we'll be taking some example for that. You can see I have taken on X, which will be having uniform distribution that's varying from 0 to 10, and I'm taking mid X to follow normal distribution 1 to 2, and spread X following uniform distribution from 0 to 10, and epsilon is the error that's following 0 to 1, and spread epsilon follows to chi-square distribution. I have constructed some data. From the data, I try to fit the model. The actual value, the actual connection between x and y is given by this. You can see this equation, y equal to 2 mid x plus 2 spread x plus mid x square plus epsilon. This is the simulation I am doing. Therefore, I have got my y by doing this relationship, by taking this relationship where epsilon is some error. That error, what actually the errors are, that's what is given here. That we follow normal distribution with the 0 to 1, 0 mean and 1 variance, and the spread of epsilon will be chi-square distribution. We have generated y. So when we have collected this data of x and y, when I try to use my model, that is giving me this equation 1.91 mid x, 2.22 spread x, and 1.09 mid x square. You can see 2 mid x, 2 spread x, and mid x square. That becomes like this. So error will be there. Error cannot be foregone completely as far as regression is concerned, but I could see that error is minimum. We have some justified procedure for that, and I have taken some real-time example also. Real-time example we have taken, you just see to that this is quite interesting. Diastolic blood pressures and systolic blood pressures are taken from certain patients, and X to be systolic and Y to be diastolic, and they want to connect. Will there be connection between systolic pressure and diastolic pressure? That's done by taking 59 patients out of 3,000 patients coming to a particular hospital in some other country, in European country. And this work was already done by a researcher. Therefore, we have taken that just to see that our method performs well. The range of variation of pressure of each person over one day can be modeled by means of real compact interval. Okay. Then you can see systolic and diastolic pressure in a day you take, that will vary from minimum to maximum. Therefore, it can be considered to be a interval value data. By taking that interval value data we have done, and you can see this is a model that we have done already by the previous researcher Blanco Fernandez. alpha mid x into 1 plus or minus 0, beta spread x into 0 plus or minus 1 plus gamma into 1 plus or minus 0 plus epsilon. And he has found finally that the equation becomes like the 0.4257, etc., etc. Remember, the point now is this is not enough to predict with minimum error. I am just telling that if you are adding that x square term, mid x square term, your prediction will go pakka. That is required essentially for certain problem. That's what they are trying to do. You can see that points are plotted by taking mid values. This is only for mid. By taking mid values, when I plot it, you can see that the green line is the one that is predicted by the earlier one. But you could see the actual pattern will be a parabola. That's what is.
Excuse me, sir.
Yes, sir.
Please conclude in 1 minute, sir. Please.
1 minute, sir. Done. Over. This partial polynomial results. R squares are model 1.43, whereas model 2.485. So press statistics is 51 and 55 there, and 51 for second model. So second one should have higher R square and lesser press. That is an error. Press means an error, some sort of error. Yes, that is justified. And compared by taking one other model by taking spread x square also, you can see by considering partial polynomial model, we are getting the best.
Okay,
Error,
sir.
error is minimum here, and error for spreader is also minimum for this. This is the conclusion of our effort. Therefore, when there are intervals, it's not necessary that intervals of input and output must be connected only by linear relationship. You can add x square to enhance the model better.
Yes, sir. Yes.
Error. That's it. Thank you, sir.
Okay, sir. Thank you, sir.
I'll wait.
Any doubt from participants? Any doubt?
Professor, thank you very much for accepting our invitation, and your talk was very interesting and very informative.
Hello.
Wholeheartedly, thank you very much, Professor.
Thank you so much, sir. Thank you so much for all the audience, and thank you so much for the organizers. Thank you so much. I'll wind up.
Any questions from the audience? Professor, no questions. Thank you very much.
Thank you, sir. Thank you.
Rasmi madam, did you join? Rasmi madam? Vatsala, join madam. Hello madam, good afternoon.
Hello.
ಈಗ join ಆದ್ರೆ
Yeah, good afternoon. Is it audible?
Hello?
Hello.
Madam, very good afternoon.
Very good afternoon. Is it audible?
100% audible, madam.
Okay.
Madam, thank you very much.
Welcome.
Yes. Now I request Professor B.J. Girisha sir to chair the session.
Yeah.
Very good afternoon, madam.
Good afternoon.
So it's my privilege to introduce Professor Rashmi Bharadwaj madam, professor working as professor in University School of Basic and Applied Sciences, Guru Gobind Singh Indraprasth University, Dwarka, New Delhi. She had pursued her PhD degree in 1997 from University of Delhi. She has 27 years of teaching experience as well as research experience. She supervised 11 students for PhD degree, and now 6 students are working at present. So she has more than 100 publications in national and international reputed journals, in Scopus and Web of Science journals, and she has wrote 2 books and edited 1 proceedings of international conference, and she has subject reviewer for many international journal of very reputed, and life member of several international organizations in the sphere of mathematical sciences, including Indian National Science Congress, and she has attended and delivered several lectures in national and international conference across the world. So our field of specialization includes celestial mechanics, dynamical astronomy, nonlinear dynamics, ordinary and partial differential equations, numerical analysis, and others. So she has visited several countries in her experience, like UK, Drexel University, and then Turkey, Istanbul, Commerce University, Istanbul in 2005, and Suntec University, Singapore, and Netherlands, Eindhoven University of Technology, and many other countries, even including Australia. So Sydney University, Australia, and many other countries. And also, she has recognized in, she has awarded many fellowships and awards. So mainly, Indian Meteorological Department awarded 27th Biennial Museum Award in 2013, and she has awarded Best Researcher Award for 3 consecutive years, 2013, 14, 12, 13, and 11, 13, and Best Teacher Award in 2011, and many awards. There is a big list of awards, and she became member of many bodies like life member of American Mathematical Society, Indian Science Congress Association, Indian Mathematical Society, Indian Society for Industry and Applied Mathematics, Gwalior Academy of Mathematical Sciences, and Oceanic Geoscience Society, and many others. With this brief introduction, I welcome Bharadwaj Madam to deliver lecture. Madam, thank you, and please.
Thank you very much.
Please carry the session, Madam, please.
Just a minute.
Okay, Madam, okay.
Hello? Hello?
Hello, ma'am.
Yeah, is it visible?
Yeah, ma'am.
Hello?
Yeah, ma'am.
Okay. Thank you very much and for giving me an opportunity to address to this enlightened gathering. Today I kept my topic to be related to the COVID-19 modeling. So it is a fractal neuronal wavelet hybridized modeling of COVID-19. Just a minute. So what is the basically a mathematical modeling? So in general, if we have to talk about the mathematical modeling process, it is any real world problem which we simplify as a working model. Then we represent it as a mathematical model, translate this mathematical model into a computational model, simulate this model and then we find out the results and conclusion. And these results and conclusion again we interpret in terms of the real world problem. So in the mathematical modeling problem or process, the two things are important. How we simplify the real world problem as a working model, and again the results which we got, how to interpret in terms of that real world problem. Then only we have the sense of this modeling. Otherwise we will stuck out in between of that. Now what are types of the mathematical model? There are basically two types, empirical model or the theoretical model. If we are talking about the empirical modeling, so it is of two types, experimental modeling and the observation based. But if we are talking about the theoretical modeling, so it is three types, either it is statistical or mathematical or a computational way. Now in general form, any real world problem, we interpret through mathematical language. The mathematical language is applicable for the three types. Either we collect the data, or we develop the continuous equation, or define the discrete characteristics. Based on these, we design the model using the governing parameter, then find the analytical, numerical or asymptotic solution as per which kind of the equations we are dealing with, analyze the solution, predict the future solution, then we find out or validate the data, implementation of result, and again interpretation in terms of the real world problem. So to start with, I have to, because this is a fractal based modeling. So what is fractal? Suppose we have a plus sign. On each side we are putting a plus sign. So this is the first iteration. Again on each line put the plus sign. So see that in the third iteration how complex structure we got it. But the beauty of this structure is if we take a small part of this and zoom in, we are getting again the original structure. So this means any simple structure we are developing a complex structure or the complex to the simple structure. We study the small part and then we correlate with the complete structure. So in short, fractal is an extremely irregular line or surface formed an infinite number of similarly irregular sections. It is a rough or fragmented geometric shape that can be subdivided in parts, each of which is a reduced or size copy of the whole. And mathematically, it is a set of points whose fractal dimension exceeds its topological dimension. Now, how we have to generate the fractals? Basically, it is the iterative or the algorithm or the formula based. So, how we have to take it? Suppose we have a straight line, divide this line into three parts, remove the middle part, and instead of that, join with the two straight lines. Now, this is a one iteration. Now, we are applying the same on each line, here, 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 and here. So, we got this one. Again, apply on each line, like this, and like this. So, we got all these and see that in the fifth iteration, how complex structure you got that. But any small part, if you zoom it, it looks like the original structure. So, how we have to find out the dimension? The simple way is D is equal to log of number of new pieces divided of number of the original pieces. So the new pieces are 1, 2, 3 and 4 and original are 3 pieces. It is log 4 by log 3 which comes to be the 1.26. So these are the dimension which is neither one because it is not as line and as it is not complete triangle, so it is in between 1 and 2. So the dimension comes to be in the fractions and this is known as a fractal or the fraction dimension. So for this and this Cosh curve, this is known as mathematically as a Cosh curve and it is nowadays used in all our telecommunication purposes. So our mobile has the chips which are of this Cosh curve form. This process started with the Cantor. Cantor, already we know the Cantor set that any straight line from 0 to 1 divided into 3 parts, remove the middle part and instead of that again repeat this process. So Cantor is repeating this process to find out whether this solution goes to infinity and in between he left this problem and said that it is the mathematical monster. So this is the earliest form of a fractal because you are getting the pattern which are self-repeated. Now I am taking a very simple example. Take a triangle, join the midpoints of the triangle and remove that like this. Now so original triangle is 1, we have the one picture. Now we have the size as a half, but we have the 3 triangles. Now again repeat the process and see that the dimension comes to be the 1.585 and this is the figure which is a completely hollow picture but it absorbs the maximum area and so nowadays it is used in the telecommunication purposes also, but the beauty of that it has all kind of the triangles, all size and if you zoom in any part you are getting the original picture. So these are the now the pattern which is repeating itself. So these are the, there is no typical size of the object, length scale. So it contains triangles of all possible sizes and of course the practical limitation are there. The size of the entire object depends on the number of the iterations, how many iterations we are taking in. If we are talking about our human body, so in our human body, if we are talking about the bronchial tubes, These has the dimension very close to 3. Our arteries has a dimension as 2.7. Our brain has a dimension as between 2.73 to 2.79. Our alveolar membrane has the dimension as a 2.17. Nowadays, this chromatin is the fibrous material inside our cells nucleus, which contains the genetic material from clusters which has a fractal dimension. Nowadays, the research is going on to find out the fractal dimension of this material. So, chromatin material, if we are able to find out the fractal dimension of this chromatin, so at the early stage we are able to detect the breast cancer. Now this is a fractal antenna which I showed you. This has a 5 type of the triangles, and this is the Sierpinski triangle which we joined, and see that 1, 2, 3, 4, 5, and this antenna nowadays we are using this in our mobile phones. This covers or contains all kind of the information and all kind of the signal it captures. If somewhere the signal drop from here, so it absorbs from here. This is the Koch curve which already I showed, and it is a part of the chip which is we are using in our mobile phones. Now how we have generated these things? So simple, I am taking an example. Suppose x equal to x square plus 1. As if you are taking this example, left hand side is 1. If you are putting left hand side as 1, then you are getting the right hand side as a 2. Same way, 2 if you are putting, you are getting a value as 5. 5 if you are putting, you are getting a value as 26. If you are putting 26, then it is 677. And like this, it is continuously going on. Mandelbrot is the first one who used the IBM computer to generate this solution, and he plotted this equation x equal to x square plus c. The beauty of this curve is it is an open curve. It is not a closed curve, and it is repeating the pattern within pattern. Now if you see, this is the Mandelbrot set. If we zoom in inside of that, we are getting the similar picture like this. Any thread, a small thread you take that, zoom in, you are getting a picture of the same size. And again a small thread, if you zoom in, you are getting the similar picture. So this is the important that in our body we have the cells which are repeating itself. That's why we have the cell generating processes. Now what is a bifurcation? It is basically a division of a one cell into the two cells, or from one to the two units. I am taking a very simple example. Suppose you have this equation xn plus 1 equal to r of xn into 1 minus xn. Here are the two parameters. One is the parameter r, and the another one is the initial value as a x naught. As we are changing these parameters, we are getting a different shapes. Now if r is 0.5 and x naught is 0.5, you see after some iteration it goes to the 0. Same way if we have r is 0.8, it took a longer but it again goes to 0. R equal to 1.0, again the same way. But if I am coming to r equal to 1.5, then you see that it is terminating or going towards the constant point, which is a fixed point. Same way if you are taking r equal to 2.5, it is going towards the 0.6. But if you are coming to r equal to 3.2, then you see it is bifurcating into two parts. Either this or this, or this or this, or like this thing. If you are taking 3.5, then it goes to the 4, and like this, 4 to 8. So this means cells are dividing. So one cell, 1 to 2, 2 to 4, 4 to 8, like this thing. And this is also a tumor growth model. So if a doctor has to do the chemotherapy session, suppose they are doing here. If they are doing here, then this cell goes, but this growth is there. But instead of this, if they are tackling this part, then the complete growth goes to. Same way if they are tackling to this part, then only this goes, this is there. But if they tackle to this part, then it complete goes to. Same way it is this one. Now this is a Sierpinski triangle, which is also a bifurcation model. So this is a most affected part, which has the, see the how complex structure we are getting on the surfaces. As in the COVID, the most affected part is our lungs. So this is a lungs canopy, which is also a fractal part. This is the new generation or the new converging technologies which we are using nowadays. Earlier we are studying about the biological sciences or nanotechnology or cognitive sciences or information technology, material sciences. Now we are dealing with the combined of these, all these type of the therapies.